So good morning and welcome to the workshop. My name is Cecilia Solhoff. I am an outreach specialist in the Wireless Telecommunications Bureau here at the FCC. There's a couple of housekeeping items I want to go over before we get started. We are broadcasting this session live on the web. For those of you who are listening to the live stream, you can submit questions to the moderators by sending an email to livequestions@fcc.gov. We are asking that you please include your name and the organization you're affiliated with your question in your email. For those of you sitting here today, with the handouts over there, we have some index cards and pens, and Michael in the middle here in the bright blue shirt has them with him also. So we're asking that you write your questions down on the note cards and just raise them in the air when you're ready. And please include your name and the organization you're affiliated with your question as well. And please don't wait till the end of the panel. Go ahead, anytime you think of a question, submit it. And given time constraints and the volume of questions, the moderators will try to get to as many questions as we can during the workshop. And now to get us started, I'd like to introduce Ruth Milkman, who is the Chief of the Wireless Telecommunications Bureau.
Thanks, Cecilia. Good morning. On behalf of Chairman Janikowski and the Federal Communications Commission, I'd like to welcome everyone to the FCC's workshop on issues affecting the interoperability of customer mobile equipment in the 700 megahertz commercial spectrum. This workshop deals with highly technical issues. Witness our selection of moderators for the first panel, the Chief Engineer of the agency and of the Wireless Bureau. But these technical issues have obviously very important policy aspects. Interoperability in a variety of contexts is something that the Commission and stakeholders have highly valued. And as the Commission works to facilitate the development and deployment of affordable mobile broadband to all Americans, interoperability can play an important role by helping realize economies of scale and thereby lowering costs, and by enabling roaming, which increases competition and allows consumers to stay connected and in touch when they travel. Demand for mobile broadband continues to increase sharply, and ensuring the most productive use of the 700 megahertz band will be critical to reaching that demand. But in seeking to achieve these goals, we also have to take into account the realities of engineering, economics, and other practical considerations. The 700 megahertz band reveals some of the complexities of deploying wireless networks. 700 megahertz band, as you are well aware, is really two separate bands, the upper and the lower 700 megahertz bands. And this is significant because a mobile device must include unique radio frequency components for each band it supports. In addition, as with any band, there are adjacent users that must be considered, and factors such as cost, complexity, interference, handset size, and battery life must all be taken into account by manufacturers and by network operators. There have been a number of important issues raised with respect to the development and deployment of 700 megahertz equipment. In August of last year, the Chief Engineer of the Wireless Bureau, Tom Peters, began attending the standards meetings where technical issues related to the deployment of LTE, the overwhelming technology choice of licensees for this band, have been discussed and debated. And progress has been made in the standards process to enable products that would not otherwise be available. However, issues do remain in the standards process and in the commercial marketplace, and the Commission staff, led by the Wireless Bureau's Chief Engineer, will remain engaged. I'm confident that improvements in technology will bring progress. I also hope that the discussions we have today will help bring about a better understanding of the issues that still must be addressed. Our program for today includes two panels. First, a panel to address technical issues related to interoperability in the 700 megahertz band, such as the status of standards development for the various band classes, chipset capabilities, interference from adjacent bands, and the implications of developments such as carrier aggregation. Following a short break, a second panel will examine factors affecting the market for 700 megahertz handsets, including a discussion of costs, capabilities, and the ability of smaller operators and their customers to acquire competitive handsets, as well as public interest concerns, such as promoting access to broadband for all Americans, including those who live in rural areas. We have assembled an excellent group of panelists, and we look forward to a robust and productive discussion. Thanks to all our panelists for being here. Thanks to all of you in the audience and watching on the web for attending this workshop. And now I'll turn it back over to Cecilia, who will introduce the moderators for the first panel.
Thank you, Ruth. So the moderators for the first panel will be Tom Peters, who is the Chief Engineer in the Wireless Telecommunications Bureau, and his co-moderator will be Julie Knapp, who is the Chief of the Office of Engineering and Technology here at the FCC.
Thank you, Cecilia. I'd like to also welcome all of our panelists to join me, and as well as Julie for joining me as a moderator of what I expect to be a very fascinating discussion about interoperability technical issues related to the 700 megahertz band. So let me start by introducing our distinguished panelists. First to my left is Gene Fong. Gene is a senior staff engineer at Qualcomm CDMA Technologies, QCT. Gene also represents Qualcomm in the 3GPP RAN 4 working group meetings, which develop the minimum technical standards for equipment deployed on frequency bands worldwide. Gene is intimately familiar with the technical issues in the 700 megahertz band, how these issues have been handled in the standards process, and also how these bands will need to be implemented in mobile devices, what needs to take place in order to realize these bands. So thank you, Gene. To Gene's left is Doug Hislop. Doug is a partner at Wireless Strategy, a wireless technology consulting firm. He's a wireless technology expert who has co-authored several papers on this very subject, the subject of 700 megahertz interoperability. As a consultant to a consortium of companies and industry groups that generally represented the interests of the smaller 700 megahertz licensees, Doug provided papers that challenged many of the technical assertions that were made by other companies, some of which are represented on this panel. So we look forward to hearing from Doug and his thoughts on the technical issues here. Thank you, Doug. To Doug's left is Bill Stone. He's the Executive Director of Network Strategy at Verizon Wireless. And of course, Verizon Wireless was one of the major winners of 700 megahertz spectrum in Auction 73, the 700 megahertz auction, and holds a nationwide license in the Upper C block, of course, as well as several licenses in the lower part of the band. Bill's team is responsible for advanced technology planning for Verizon Wireless, including the development of network evolution plans, participation in industry standards groups, and spectrum planning. Thanks, Bill. To Bill's left, Paul Kolodzy, of a wireless consultant to Vulcan Wireless. Dr. Kolodzy was formerly a senior spectrum policy advisor here at the FCC, also was director of the Spectrum Policy Task Force. He's currently active in technology development for 700 megahertz commercial and public safety spectrum policy, as well as interference mitigation technology. He's here today representing Vulcan Wireless, a 700 megahertz lower A block licensee in the Pacific Northwest. And finally, last but not least, Edgar Fernandez, distinguished member of technical staff for Motorola Solutions. Edgar wins the prize for making the longest journey here to join us on the technical panel, having come from his home base in the UK. But I believe he's participated in both ETSI and 3GPP standards activities for over 20 years, so he's used to long distance travel on short notice. So thank you. Thank you for coming. Regardless, we're lucky to have Edgar because he's got over 30 years of experience in RF engineering, RF design, product development, systems engineering, and regulatory approval. And he's been the 3GPP RAN 4 working group vice chair since 2007. He has both deep and broad knowledge of spectrum and interference issues related to the 700 megahertz band, and as well as the potential consequent impacts on the design of mobile devices in this band. So thank you, Edgar, and thank you to all our panelists for joining us here this morning. And let's start things off with Gene Fong to give a short 5-minute introductory statement on his thoughts on this panel. Go ahead, Gene.
Okay. We have slides.
Slides are up. Maybe you can see it there.
Oh, okay. Thank you. Firstly, I'd like to thank the Commission and Tom for the introduction and for extending the invitation for us to attend here and giving me the opportunity to speak to you all and to participate in this panel discussion. As Tom mentioned, I work as a systems engineer for Qualcomm. I also participate as a representative for Qualcomm in the 3GPP RAN 4 working group. On the first slide here is my email address if you should want to get in touch with me later. For those who may not know, this second slide is basically a description of Qualcomm. We're a leading chipset provider. I won't go into more detail on this one. So starting off, Qualcomm chips are all multi-mode chips and multi-band chips, meaning that these chips are designed to be able to support LTE, 3G, 2G across multiple bands. Our goal as a chipset provider is to provide as much capability and band support as possible within obvious size, costs, and other constraints of the chipset. Unfortunately, today, our chipsets have a limitation in the sense that we're able to currently support no more than 2 bands below 1 gigahertz and 3 bands above 1 gigahertz. And as a result of this limitation, Qualcomm is not now able to support more than a single 700 megahertz band in addition to, for example, say the cellular band. However, Qualcomm continues to work towards extending the capabilities of the chipset, and one of the areas that we're looking into, for example, is the 700 megahertz band that we're talking about today. And in so doing, we've identified a number of technical challenges that for sure are non-trivial, and I've grouped these into lower 700 for bands 12 and 17, and upper 700 for 13 and 14. So here on the next slide, we have a diagram that represents the lower 700 megahertz. And there are 3 figures here, and they represent 3 different scenarios. The first one is a band 12 scenario, the middle one is a band 17 scenario, and the bottom one is a band 12 and 17 with supplemental downlink type condition. You can see that on this diagram, common to all 3 of these on the left-hand side, or the lower part of the spectrum, is the channel 51 high-power broadcast signal. And you can see that this very high-power transmission with its side lobes, basically the out-of-band emissions from this transmission we feel can possibly generate interference into the lower part of band 12, into the A block, specifically into the base station receiver. Another issue that we've identified is that in channel 55 and 56 with the broadcast 50 kilowatt transmissions. If you take a look at the uppermost figure, in 3GPP we've identified some of these issues here, and we've addressed them. For example, we've introduced a 1 megahertz guard band at the lower edge of band 12 to allow for greater opportunity for filter transition. We've also introduced a compromise suboptimal solution for the channel 56 blocker, in the sense that the blocking requirement is the traditional ACS requirement in 3GPP. Now, if we take a look at the middle diagram represents a band 17 case. Band 17 consists of B and C blocks, and so it's narrower, and because of that, for example, the channel 51 interferer doesn't affect it so much. Furthermore, you can see on the downlink, you can see there's a red trace here that represents a receive filter for band 17 implementation. And you can see that with the extra guard band afforded by block A, that this gives opportunity for this receive filter to be able to get good attenuation of the interfering signal coming in channel 55 and 56 in particular. And so that provides good performance in the downlink. Overlaid on top of this is a green trace, and this represents a band 12 filter if we wanted to do a 1217 in a common implementation. And you can see from this figure that, of course, the passband has been extended to include A, B, and C blocks. And you can also see in this figure that the green trace doesn't do as good of a job attenuating the interference that may come in from channel 56. So that's another issue that we need to consider. We've also noted that co-location has been suggested as a possible solution to this issue. And while it can help in some instances, we feel that it doesn't completely address the problem, and there are a number of practical challenges associated with it, primarily because we're talking about two dissimilar systems here with different cell topologies and so forth, and so that we don't necessarily feel is a complete solution. Lastly, on the bottom figure is the situation where if we were able to replace the channel 55, 56, 50 kilowatt transmissions with supplemental downlink, such as what AT&T is considering. If we were able to do that, and if DISH were able to follow suit in channel 56, then we would be reduced to the condition of the typical cellular type deployment, where we have base station transmissions on D&E block rather than 50 kilowatt transmitters. In that case, then we could go back to 3GPP and justify that the adjacent channel emissions, the adjacent channel selectivity and in-band blocking could be just maintained as the traditional type of blocking levels that we have, and the band 12 filter could then give good performance in this band. Thanks. So then we get to the upper 700. On the upper 700, again, I've got three figures here. In the topmost figure, we have the band 13 situation as we have today, and you can see that there's good separation between the uplink and the downlink. As such, I'm able to put a band 13 transmit filter, for example, over the uplink shown in the green trace here, and with that filter, I'm able to get good insertion loss, meaning small insertion loss within the passband, and yet good rejection to provide good UE coexistence performance in the band 13 and band 14 downlink, and to some extent some protection into the public safety narrowband from 769 to 775. So that situation works pretty well. Now if we take a look at the middle diagram here, first and this is in consideration of combining band 13 and 14 together. If we take a look first at just band 14 by itself, we can recognize, not shown in this figure, but we can recognize that there's a challenge in band 14 and simultaneous GPS performance. The second harmonic from band 14 transmission actually can interfere with simultaneous GPS reception. So if we were to combine a 13-14, obviously this would inherit that challenge. In addition, because we've now increased the passband of this device to 13 and 14, you can see in the blue trace here that the transmit filter now has to be wider to accommodate, and yet somehow still provide the same amount of rejection needed for the coexistence between band 13 and band 14, and some protection to the public safety narrowband. Of course, as we know, as we increase the passband like this, it becomes much more challenging to build this filter. To be able to simultaneously get rejection that we need for coexistence and to maintain good insertion loss within the passband becomes increasingly difficult, and that's one of the challenges that we encounter here with this situation. Oops. So I hope this gives a brief overview of some of the interference conditions that we're taking a look at, and that concludes the presentation. Thank you.
Thanks, Gene. Doug?
Hi, again, I'm Doug Hislop with Wireless Strategy. I'd also like to thank the Commission for inviting me to be here today. I'd like to go straight to the presentation. I have several slides. The first one shows the 700 megahertz band with the 3GPP band classes overlaid on top of it. The directional arrows show the direction of transmission defined by 3GPP. So an arrow pointing up is a device transmission, arrow pointing down is a base station transmission. We do note 4 specific areas of focus where interference concerns were raised previously, which led to the definition of different band classes within 3GPP. Starting with the lower band, the first concern, as Gene mentioned, was channel 51. I do want to point out that if you look at the direction of the arrows, the device receive itself is 30 megahertz away from channel 51. So there is quite a bit of room for filtering any direct interference concerns from that channel. There is a reverse power amplifier intermodulation concern. I'll talk about that a little bit more on slide 2. The other issue in the lower band is, as Gene mentioned, lower D&E, high-power broadcast transmissions. There as well, we are encouraged that with media flow moving behind us and other uses of spectrum of the D&E blocks coming to the forefront, that any concerns about interference from those blocks will also be going away. In the upper band, two of the issues that have been raised previously, one of them was, as Gene mentioned, a device transmit interference into the public safety narrowband receive blocks. Our view is the filter, if you look at the edge of transmission there, the upper C block edge is nearly directly adjacent to the public safety narrowband blocks. There's 2 megahertz away. A filter that would cover either band 13 or both band 13 and 14 would provide a relatively similar roll-off across that band. And so the issue really needs to be met with emission mass, which in our view, the emission mass does take care of that. Then the fourth issue is GPS harmonics. There is a 1 megahertz portion of the 700 band where the second harmonic would hit the GPS receive frequency. So there are some other issues that, so there's some equipment capabilities which we think will help negate that from being a concern, as none of the current blocks up there would actively transmit within that 1 megahertz. Moving on to reverse power amplifier intermodulation. That's a lot of words. Basically, there's a high power channel 51 transmission, and the supposition is a very strong signal would be present at the device antenna. It would traverse the antenna, go through the duplexer, and assuming the power amplifier of the device is transmitting at a high power, then it would mix with the strong channel 51 signal, create intermod, which could then impact its own device receive. We do feel that the equipment specifications are sufficient, and there are some other means as well which would help to reduce any interference concerns from that approach, and we can talk about that in the workshop. Lower D&E, very busy slide, but at a high level, there were high broadcast transmissions there. Those transmissions are being phased out. We expect that to be a more cellular-like type of use in harmony with the lower A, B, and C blocks, removing that as an obstacle to band 12. In terms of upper band, this graph shows very briefly our roll-off comparison. This is a graph courtesy of Avago Technologies showing a band 13 filter versus band 13 and 14. And as you can see, it's a very similar roll-off within the public safety narrowband blocks. So we view that as providing similar performance from that perspective. Then the second harmonic interference issue, if you just want to focus at the graph on the very bottom of the page, that's also courtesy of Avago Technologies, and it shows that there is a significant amount of rejection of a second harmonic that would be generated. That would greatly reduce the impact of any GPS harmonics hitting the receiver within the device. So in conclusion, we're comfortable that the lower 700 megahertz band devices should be using band 12. We view the likelihood of channel 51 interference as being a very low probability. Lower D and E block interference is going away. The 700 megahertz band devices in the upper side could use a newly defined band class that would cover both 13 and 14 as well. And there are some market benefits that I'm sure you'll talk about later in the morning associated with simplifying the band classes within the 700 megahertz band. Thank you.
Thanks, Doug. Bill?
Once again, thank you for having me, and I'll jump right in as soon as the slides come up. I think everyone knows Bill Stone from Verizon. I'm going to kind of rise above some of the technical detail from my opening remarks and come back and dive into a lot more technical depth as we go through the Q&A. But I wanted to speak in general to the multi-band device issue for starters. First thing I want to say is that we are highly motivated to support multiple bands, and I'm speaking from an operator perspective now, to support multiple bands in the device. First, many of you are familiar with the growth rates in data. As we continue to experience growth as we did on 3G, looking into the future on 4G, we absolutely plan to keep up with demand by utilizing additional bands. So there's a very strong motivation and incentive to use additional bands to enable us to add capacity to the network. In addition to the capacity driver, there's also the driver to support additional bands to enable customers to go to other parts of the world where different band plans are in use, and we want to enable devices to roam internationally. So there's already strong motivation and strong desire to support as many bands as is practically possible. Now, as any good engineer will tell you, there's always trade-offs. So I'm coming at this more from a network perspective. You know, as Tom described in my introduction, I work with our device team very closely, and they come back at me with all the various challenges associated with adding bands to the device. I personally think the biggest challenge is the size of the device. Each band you add to the device requires additional components, and exactly how much volume is consumed varies by the exact example we're talking about, how many bands are already in the device, what band you're trying to add. But in general, the lower frequency bands are more challenging because of the size of the components. You need greater separation between the antennas. Those of you that are familiar with LTE know that we use 2 antennas for MIMO. You need greater separation to achieve the isolation characteristics you're looking for to get the MIMO performance. The antenna itself is larger, so at the high end, that can add up to like 10% or more in additional volume for each low frequency band you add to the device. Those of you that think in square millimeters, that can be on the order of like 50 square millimeters. So it's a material impact on the size of the device. In addition, there's the additional cost, and then also performance. As we add additional bands to the device, we have to make trade-offs that will impact performance, especially in edge of coverage areas, to achieve these fall-off characteristics we're talking about on the filter curves. You often have to make other compromises with insertion loss and things of that nature, which affect your battery life and ultimately the performance of the device in edge of coverage. And this all leads into the key point I want to make here in the opening remarks, is that ultimately, you know, we have this internal debate. I want more bands, and you know, there are challenges with adding bands to the device. Ultimately, it's the customer who's making this decision for us. They're the ones that are deciding with their feet, you know, what size device they're willing to purchase, how much they're willing to pay, and that's what's ultimately driving this decision, is the desire to create and put at the point of sale a competitive device that meets customer requirements, that balances all of the trade-offs that I just mentioned here. So there's a very strong market-driven solution to the problem. Now, the other thing I want to point out is we have another consideration, as Tom mentioned, that we hold spectrum in the lower part of 700 megahertz as well. Just want to show you a quick picture. Channel 51 is currently deployed and implemented in many parts of the country. Now, the primary issue here is potential interference to the TV receiver itself. RUE transmit is directly adjacent to TV 51 receive. So the FCC rules specifically require that this A block spectrum not get used within roughly a 60-mile radius of every channel 51 location. So what we're showing here on this map are exclusion zones where channel 51 cannot be used. This is just another complicating factor that needs to be resolved before the lower spectrum can be put to its full use. So the closing remark on this is that we fully support the CTIA/RCA petition to freeze additional applications. Channel 51 applications are still coming in, and Channel 51 stations are being deployed. We need to put a stop to that, and we look forward to working with the FCC to resolve this issue of exclusion zones. Thank you.
Thanks, Bill. Paul?
Hi. Again, thanks, as with the other panelists. Thanks, Tom. Thanks, Julie, for the opportunity to be here today to discuss some of these issues. I'm not going to use any slides. For those who know me know that's kind of unusual. My efforts as of late have been mostly on interference analysis and the use of different advanced technologies to provide options in addressing deployment challenges. And so that's what we're actually talking about here. We talk about interoperability, you're talking about those deployment challenges. Basically, the challenges that affect us in the 700 megahertz are basically very unique to the United States because there is no other band classes around the world in this area at the present time. And so therefore, some of the arguments that we're having here and some of the issues of interoperability are actually critical because the marketplace to actually be able to take advantage of multiple devices is limited only to the United States. Interoperability, therefore, is very important for us to build that ecosystems where the systems can be both affordable and the access is plentiful to the spectrum. Therefore, we need to aggregate our users so that many users can use the same components, getting the purchasing power to reduce the costs. The standards bodies, as we've been talking about up to this point, are used to basically provide that aggregation point, to basically bring a common set of rules that are across multiple licensees and multiple bands. That allows that multiple commercial operators, which is part of the discussion here, can actually take advantage of the same components, but also between commercial and non-commercial operators, like with public safety, which is another discussion for Band 13 and Band 14. We have a variety of challenges that are ahead of us right now that we're trying to deal with. One of them is that we have some places where we have two standards, in a sense, with band class 12 and band class 17 that actually are operating in the same frequency bands. And so that's kind of an interesting challenge. One of them actually provides interoperability between all the different blocks in lower 700 and one that may not allow the interoperability. And the reason we have these issues is because we're different ways of trying to address interference and the way systems and different companies try to address those interferences. And I think this interoperability workshop is trying to take a look across the entire 700 megahertz band and address, I hope, the challenges and the opportunities in trying to actually provide interoperability. To do that, you have to address the interference issues. Practically all systems have interference issues. We all experience BlackBerries dropping, or more importantly, your BlackBerry actually causing buzzing going on in microphones and speaker systems. So we've all experienced it. We can't say it doesn't exist. The technical rules that the FCC puts together, is to provide licensees some assurance that other users will not cause harmful interference to their equipment. And obviously then, if it's not to their equipment, it won't actually cause interference to their users. But it's really a statistical calculation, and this is where I think we have to discuss a little bit of this, meaning the rules attempt to make sure that the chance of interference is small, but the definition of chance is actually very subjective as to what exactly is considered to be a lot of interference. The potential interference, though, is addressed in many ways, such as with technology, with deployment methods, with tolerance to interference, and with standards in the sense of not to actually use certain bands in certain ways. We can use different technology pieces in the sense of such as filters, amplifiers, signal processing, and these may add cost, but the question is exactly how much cost do they add? Sometimes we talk about cost in very relative terms, like 5% or 10% or 20%. We don't ask the question, what is it to the total cost of the system? And that's some of the things we should talk about here, is look at the system as a total. And that's why I'm glad we have system engineers and network engineers talking about that. Second of all is the deployment methods that we can use can actually say what are the number of base stations do you want, the placement of the towers, the power levels that you'll use. Those are all variables. In fact, part of the 700 C block in the standards was based upon actually the way we actually dealt with the how much transmit power was actually going off of the handsets. And so being involved in the standards committees actually allow you to understand some of these issues. And finally, tolerance, meaning how likely and how often will interference occur, and the methods like switching to other bands or operating through the interference actually has to be looked at. So as Doug had pointed out a few minutes ago, the statistics may point out that when you take a look at some of these things, how often do they occur, and is the operators willing to absorb that? And that's actually an operator question as to how much are they willing to accept, and exactly what the balancing act is between giving the customers the purchasing power across all these bands as well as providing interference protection. And so in some sense for upper band 12, lower 12 and lower 17, in a sense band class 12 and 17, those are some of the issues that are coming. What are the chances that to occur? So at the end, to summarize, what I think we need to do is address these issues and balance these challenges with opportunity to make sure that we ensure the opportunities to build an ecosystems for the users. In one respect, we need to basically provide interoperability like using band class 12, and also we need to be able to create opportunities for additional interoperability, such as with band class 13 and 14. Thank you.
Thanks, Paul. Edgar?
Okay. Okay. First of all, I'd like to thank Tom Peters and the FCC for this invitation to appear on the panel. Slides. I'm currently involved in developing the RF specifications to cover wideband CDMA, HSPA, LTE, and LTE Advanced. Since this work takes place in 2GPP, it may be useful to describe the specification process and issues relating to new bands in 2GPP. Next slide. So this is quite a busy slide, so I'll try and summarize some of the key aspects that which may have of interest to this group. Essentially, 3GPP develops open standards for the mobile communication industry. It has approximately 372 members coming from industry and comprising of regulators, governments, manufacturers, both network and handset manufacturers, and component vendors. It has 6 global partners which transpose the 3GPP specification into local specifications. These partners include Europe, Japan, Korea, China, and ATIS in North America. 3GPP specifications consist of 4 specification groups. These are the ones highlighted in red. So basically, these specification groups agree on or approve new work items, approve the output of the working groups, which do all the work, and approve any of the changes to the specification which have been addressed in the working groups. At the end of each quarter, they meet every quarter in a year. At the end of each quarter, they will release the specifications which are downloadable from the web. So RAN4 is the working group which is charged with defining the radio performances, and that's the one I've highlighted in a square brackets, if you can see on the red chart. So this is charged with defining the radio performance requirements. Output of this working group is submitted to the appropriate specification group for approval. New bands, coexistence, and regional regulatory requirements are addressed in RAN4. So we look after the specifications for the device, for the base stations. We create the new, specify the new operating bands, and we look also and include the regulatory requirements for each country into that particular operating band. And that's a mandate from 3GPP that we should include any applicable regulatory requirements. So a lot of the FCC requirements are applicable to the US bands. So RAN4 decisions are reached by consensus, and this is really a group consensus. This is really after a long and lengthy process over multiple meetings. We start at 8:30 and we probably finish about 9 o'clock, if not later. So no dinner until we close the issues. So let's go to the next slide. So like Bill, my slides are very high level, and I'd like to address the specific issues addressed in the other slides when we come to some of the questions. So again, this is a very busy slide when available. Can you use this? Okay. Okay. Okay, so when we consider the requirements for each band, we need to consider the many bands that need to be supported and the associated coexistence scenarios. Each new band takes about 6 to 9 months to complete in 2GPP. Life was easy when we started in 2GPP. We had only 2 GSM bands and 1 wideband CDMA band, at least in Europe. Today, we've got 34 global bands in the standard, which include 13 bands which are specific to the US, and these are highlighted in green. Addressing these number of band combinations in a small form factor device is extremely challenging. Now let's go to LTE. LTE has introduced a further level of performance enhancements, significant I should add, but also significant complexity in the device, mainly on the device rather than on the network side. We need to support channel bandwidths up to 20 megahertz. LTE modulation is both narrowband, because you can transmit one resource block with 180 kilohertz, and also wideband, so you can transmit 1.4, 3, 5, 15, and 20. So it's a mix of both systems, and this we need to address in the coexistence issues. Issues for both narrowband and wideband are significantly different. LTE devices have to mandatorily support 1 uplink and 2 downlink paths. So that means 1 transmission part on the uplink and 2 downlink receiver paths on the downlink. So you essentially need 3 to 6 analog filters, discrete analog components, which are band specific for each operating band you add into the device. Supporting many bands, of course, will decrease the antenna volume if you maintain the same form factor. Now, many of the channel plans that we've seen so far and we have to work with have been designed to support 2G systems and face coexistence issues when we're trying to deploy larger channel bandwidths such as LTE. For example, band 13 Band 13 is the most complex band in the 3GPP standard. It's a 10 MHz system operating adjacent to a 12.5 kHz narrowband public safety system with only 2 MHz of uplink downlink guard band. This leads to very complex implementation and significant coexistence issues. So I think I'll end there. Thank you.
That wasn't news to you, Bill, was it? No. Okay, good. Let's start the questions with a question about Band 12. As my friends in the Public Safety Bureau like to say, you can't have interoperability without operability. And I think it's safe to say that Band 12 got a slower start in both standards and device development process, slower relative to Band 13 and Band 17 devices. And I'm wondering, probably start with Eugene, if you could recount for us what happened in the standards process relative to Band 12. When I started attending the 3GPP meetings in August, I think the discussion was just starting to get heated up. There were some special late-night ad hoc sessions in that meeting in August, and then a special two-day meeting in Chicago. Eventually, the issues got resolved, but I'm wondering if you could recount for us the history there and bring us up to the present date where we are in the development of Band 12 devices.
Sure. Thanks for the question. I think when we first started taking a look at Band 12, again, most recently, there were a number of issues that were brought up. And one of the motivations was to be able to enable bringing up Band 12 and getting this up on the air. And there was a large push to be able to do this, and it was, as we started to study more closely some of the interference conditions, then we started to evaluate how we could facilitate that with Band 12 and what we may need to do, if anything, to make adjustments in the specifications to enable this. And in particular, many of these were due to the interference conditions that I previously discussed. So in 3GPP, we studied this quite extensively, and there were a number of discussions about the best way to handle this, about what the nature of the interference is, about what the capabilities of filtering was, about what projective capabilities were, also keeping in mind time frames and other constraints. And so one of the things that we did, we came to the conclusion that the right thing to do was to introduce a 1 megahertz guard band. So we redefined Band 12, which originally consisted of 18 megahertz in the passband and 12 megahertz in the gap. And we redefined that to introduce a 1 megahertz guard band at the lower part of Block A. And the reason for this was to help provide some ability for filter transition to be able to provide rejection to some of the interfering signals that may affect it. And so we saw this as a good approach to be able to help with the situation. The other thing that we looked at was the interference conditions. And one of the interference conditions that affects this band is the high power transmissions from, for example, channel 55 and 56. And if you look at the band 17 definition, the band 17 definition has a requirement that a blocker level of minus 30 dBm be tolerated within channel 55 and 56. When we evaluate this for band 12, the blocker in channel 56 is actually in the adjacent channel. It's not so it's immediately adjacent to the downlink. And so we did reach a compromise solution that in some sense is a little bit suboptimal, but we specified the requirements such that the band 12 receiver would be held to the typical ACS requirement in 3GPP as a compromise solution in order to enable quick adoption and to be able to get band 12 up on the air. And so these are the adjustments that we made to the specification. This was quite a lengthy process, numerous discussions, technical discussions among many companies to come up with what we feel were the best compromises and specifications to enable this.
And in terms of the where we are today, where do you see the time frame in which band 12 devices will become available?
So Thanks again for the question. So in terms of the specification work for Band 12 in RAN 4 is complete. So we have defined all of the specifications in RAN 4, the performance specifications for Band 12. So the specifications are complete. I believe they are also complete in RAN 5. So now it's a matter of component availability and so forth to be able to get devices available. But in terms of the specification, there should be nothing in the specification that's holding back availability of devices.
Can I comment on that?
Yeah,
just
absolutely.
very quickly? I absolutely agree. The specification work, the folks in 3GPP have done a great job doing the best they can to address the potential interference issues that crop up with Band 12. So specifications are complete. Components, based on what we're hearing from our device OEMs, are not yet commercially available. I think we're like roughly 6 to 12 months away from commercial grade components being available for Band 12. But the other point that I don't want to lose sight of here that I want to come back to is that the use of Band 12 still is subject to, and this gets back to the probabilities, but it's higher, that the probability of interference is greater with Band 12 than Band 17, as long as high power broadcast is in use in the adjacent bands. D&E, it's looking like there may be a path forward there, that the high power broadcast, and I'm sure Tom's going to lead into questions later, so I'll leave that sitting there for him to lead us into, but it's looking like the high power broadcast may go away in D&E, but we still have channel 51. The high power broadcast there, as I referenced before, the interference conditions of concern are the susceptibility of the TV channel 51 receiver in the presence of a Band 12 device, as well as, I didn't reference in the opening remarks, the susceptibility of interference at the eNode B receive that's operating in Band 12 if it's in close proximity to a channel 51 transmitter. And this also ties back to the fact that applications are still being filed, and it's very, in fact right now it's impossible to plan because there's some uncertainty as to where channel 51 transmitters will be located. So in addition to the specification work, the point is we also have to address the high power signals in the adjacent bands, with channel 51 being the biggest risk at the moment.
Anybody else want to comment on Band 12?
Yes, I'll make a comment. I think the situation with Band 12 was somewhat in a limbo state because of the cohesiveness issues, and since 3GPP works by consensus, it gives an opportunity for companies to come and say, look, we'd like to try and progress this issue and try and find some mitigation to address these issues. And certainly would thank US Cellular, who organized an ad hoc in October in Chicago last year to find a way forward. And that was meeting attended by many companies. I'll just quote some names: Alcatel, Avago, Cellular South, Cox, Ericsson, FCC, Fujitsu, ST Ericsson, Huawei, Infineon, King Street Wireless, IP Wireless, Sprint, Motorola, Metro PCS, Nokia, T-Mobile, Qualcomm, Raceband, Samsung, US Cellular Corporation, Verizon, and ZTE. Basically, out of that meeting, we came up with a way forward to try and address the issue. So 3GPP does provide the flexibility and consensus way to try and address issues as long as companies are willing to take that route. And we see other scenarios, like today, for example, Band 13 and 14, similar approaches could be taken to address these problems.
Okay, thanks.
Doug?
Sure. Yeah, I'd like to chime in as well on Band 12. So, especially on the lower D&E blocks, if you think about the traditional use of it, Qualcomm was deploying the media flow broadcast technology in the lower D block for a number of years. Media flow is a very high power technology. You deploy it on typically higher base station locations or tower heights than a cellular-like deployment. So there was some concern about receiver blocking. In our view, that could have been mitigated through careful base station placement, coordination, and just the general difference of a broadcast technology covering a wide area versus a very focused cellular-like penetration. So with media flow, Qualcomm moving away from the media flow business case, broadcast video is a tough business to maintain, especially if you mainly have 6 megahertz of spectrum. They had 5 cities in the lower E block as well. So it's a fairly limited spectral position to support that business case. With them moving away from that, we do fully expect D&E to be used for cellular-like uses going forward, and that would be in harmony with the lower A, B, and C device use and the upper side of that.
Just wanted to comment on that very quickly. The biggest challenge, if you look up here with DE to the right, the ABC sitting directly adjacent there is UE receive, and as many of you know, we have no control over where our customers are. They're mobile. They wander close to a DE transmitter, and they're susceptible to interference. So it's not something that's easily planned around, especially with mobile users.
I'll challenge you a little bit on that, Bill, because there's other cases that actually have come up where you actually know where your transmitters are, your base stations are, so therefore you can do network coding to be able to tell them when they're actually close to a 51 station. So we do have some knowledge.
I was referring to DE, though.
Oh, well, DE, okay. Well, but in some sense also, if you actually have knowledge of them. So, I mean, right now, networks are a lot smarter, in how to address some of that. The other question I have, and go back to the statistical case, is what was not understood very, very well is exactly how much power and how much interference. The big case in the sense of the lower Channel 51 case is actually this reverse PA intermod. Okay, in the sense that you're going in on the transmitter side of the intermod and then creating something. There's a lot of coupling that has to occur to actually have to make that occur. You have to have high power, you got to actually couple into the system, you have to then have an intermod, you have to be strong signal associated, you have to be on the edge of your band. When is that going to actually occur? The edge of your cell, or at least be at a high power situation. So the question is are you actually creating, is the problem really that significant, or are we trying to solve a problem that is lesser significance? And the question, if we got rid of 51, that would be all taken care of. I agree with that, Bill. I mean, if you didn't have the 51 channel issue. The second question that I have is, I'm still not understanding very well the 3GPP process. What is the difference between band 12 and band 17? When you actually have, I'm looking for the experts in 3GPP here, you have a band 12 device which actually runs in B and C block. And you have a band 17 device that runs in B and C block. Can the band 12 device actually interoperate with B and C? Or is that not going to be allowed?
Yes, it can. Sure.
It can.
No, it can't. Go ahead, Edgar.
Sorry. Maybe I missed the question.
What I'm wondering, if you have, and this is a question I think a lot of us have, okay? If you have a band 12 device, if you actually have built something that actually conforms to the 3GPP standards as being band 12, which includes the B and C block, does it have the capability of interoperating with the B and C base stations? Doesn't mean it can. We'll be allowed to for roaming or whatever. I'm just saying, can it actually technically interoperate?
Gene, you want to take it?
Yeah. I'll take a stab at that. There are a couple of differences, actually. If you take a look at the requirements for band 12 and band 17, it's true that the duplex gap is the same and there's overlap in some of the spectrum. However, for example, one key difference is the blocker requirement. So there's obviously a different blocker requirement for 17 than there is for 12. And the blocker requirement for 17 takes into account a minus 30 dBm receive from channel 56. So that's one thing. So therefore, it would be quite a challenge for a band 12 device to be able to meet the band 17 requirement as written in 3GPP specifications. The second issue that we need to consider is that a base station is capable of signaling a single band. Right. So a base station says, I'm a band 12 base station. My UE, if I'm a band 17 UE, I can't connect to that base station because it's not the same band, obviously. So there's also the issue that the base station can only signal a single band, and even though it may have the same duplex gap and perhaps the same, frequency arrangement as the other band, I'm not type approved against that band. I can't jump onto that network.
Let me jump in here. And I might add, it makes our job easier if you guys ask yourselves questions, but.
Just step to the audience.
No, but to follow up on this question, if a band 12 licensee or someone who's deployed a band 12 network and band 12 UEs then was to go roam onto a band 17 network and was willing to take the hit of the reduced protection from blocking in the E block. Is that technically feasible?
I think Gene's comment about the network only signaling one value of support is technically correct, although there is some work in 2GPP to try and address that issue. Right. And then in terms of interoperability, question is, yes, it will work on that band, but obviously you won't meet the requirements of band 17 in terms of performance. So it's really a question of what level of interoperability are you looking for. And then I assume that you'll be operating on the same channel bandwidth for both systems. So these are three issues that would define interoperability. So it's really yes and no.
Okay.
It's correct.
Okay.
But can you elaborate on what you mean by it won't meet the performance specs? What, in a tangible way, what is that going to mean?
Well, the band 17 device has a tighter requirement for protection of E block, because you've now got a 5 MHz guard band, which is A block. Whereas the band 12 device, the filter is wide open, and therefore its blocking performance will be worse than a band 17 device. So yes, it will operate, but in those circumstances where it's near a E block base station, then it would suffer worse in terms of blocking performance and will desense.
Right. And the question was, if the band 12 operator was willing to take that risk, is there anything else preventing that from technically working?
I think the issue is we still need to address the signaling issue of the base station, because the base station only signals one operating band at the moment. Although,
so isn't it possible for a handset to have software that says, if I see a band 17 network, I can translate the channel numbers, or so that it, because the bands overlap, it physically supports the spectrum and the 10 megahertz carrier that might be deployed there. So can't it just translate the channel numbers and do the work itself to overcome the network deficiency?
So I think that the way that the specifications are defined, a UE can say that it supports a certain band when it meets all the requirements of that band. Right. And for, say, for a band 17 UE, for example, that means that it can meet the minus 30 dBm blocker in channel 56. If for some reason we were able to waive that requirement or disregard that requirement, then we would make the two very similar. And in that case, we could say that, yes, this UE does support can legitimately say it supports band 12 and band 17. Therefore, whenever it sees a network of either band, 12 or 17, it can connect.
Okay, thank you.
Could I add something to that, Tom?
Oh, absolutely.
So the only difference between band 12 and 17 is the blocking specification. If we look at the direction the standard appears to be going of introducing supplemental downlink for D&E, that would not be a situation where this kind of blocking requirement would need to be carried forward. So we would suspect then that if the blocking requirement is made obsolete, band 12 and 17 performance requirements would be identical.
Okay.
Yeah, just ask a broader question. We understand it's an ecosystem here. We've got different players that are involved. There's the equipment manufacturers, the chip makers, the filter makers, the carriers, et cetera. And maybe start with Gene, and if we can, and Edgar and Bill, maybe say a little bit about how does this process work? For people who are on the outside, and this is probably the first and last time I'll ever ask about the functioning of standards committees, but how do factors like roaming and competition get built into that process, aside from just looking at things like the space I've got on a board for devices? Gene, maybe you can.
So in the standardization process, we define a number of different bands. I think Edgar had a slide there that showed 30-some bands that are currently defined. And generally, each band is introduced as a work item into 3GPP. And when that band is introduced, the proponents of the band define how they anticipate using the band. For example, it's a US band or it's a European band or something like that. And the specifications are defined around that intended usage of the band. These bands are defined in such a way that therefore then you create these coexistence requirements within the 3GPP specifications which define the band. A device then can choose to support, obviously based on demand and so forth, which bands it supports. So, for example, if it needs to be able to support band 13 and it needs to be able to roam on band X, and that device supports, then that device would need to support both those bands and the requirements of those bands. There's, at least within RAND 4 specifications, and there isn't any particular clause, so to speak, for that addresses roaming, aside from the fact that these bands are defined, they have distinct requirements, and being able to operate in that band implies that you meet the requirements for that band.
Edgar, could you maybe talk about that a little bit too? Yeah.
I think what Gene says is correct. Essentially, it's the first process is the regulators release the spectrum, and then the operators who will support that band in 3GPP, and a work item will come to 3GPP saying, can we define a new operating band for that spectrum? Then there will be a period of analysis. Once the work item obviously is approved, there will be a period of analysis to look at the issues, particularly the coexistence issues associated with that band. And then we will then define the appropriate parameters for that particular band. And that's the normal process. Give you one example of, say, similar to the band 13-14 issue here. Currently we have band 2, which is the PCS band in the States, and that proponents suggested that we should enhance that band to include the G block. So we have a extended band, very similar to band 13-14. So the proponents produced a work item to 3GPP to say we'd like to do this. 3GPP went off and studied the issues, looked at what the impacts on the legacy band 2 performance requirements, what were the impact of the enhanced requirements, and then developed a specification for that. And then it's up to industry whether they would want to choose to support the existing band 2 or the enhanced band. And that's how it works. Obviously, most vendors, in fact, all vendors and all operators would like devices to support as many bands as possible, and the goal would try and because of the complexity of supporting many bands in a device. I think that's always been the case. We try and minimize the amount of bands, except when we have a particular problem, and then we really have an issue to try and address. And this was the case with band 12 and band 17. We would prefer to have gone a single band solution. We saw problems with band 12, and the issue was band 17. Subsequent to that, we revisited the work and redefined band 12. So it's really, that's the process we go through in 3GPP. And bear in mind, there's about 374 members. There's a lot of technical advice coming to when we decide these decisions. It's not just one company driving it. The company might drive the work item, but the work item has to be approved by all the people in the group who may have, or may not have an interest in this. So there is a process, and we have expertise to now address that issue. And that's really the advantage of 3GPP in defining operating bands.
The only thing I'd like to add to that, just building on what both Gene and Edgar have said, is that it's also a highly competitive process. I absolutely agree. It's an ecosystem of players, but at each layer in the ecosystem, you have multiple competitors. Edgar just made a remark a minute ago that I would actually take exception with, that he's trying to minimize the number of bands in the device. Well, I can tell you there's tension in the system between the levels of the ecosystem, because I'd like, as I said in my opening remarks, to push for additional bands. So if anything, I'm at odds with other layers of the ecosystem where we, as an operator, we're pushing for additional bands for roaming and capacity, as I spoke about before. So we have natural tension between the layers in the ecosystem, and then within each layer, it's highly competitive. Each player in their layer, the filter providers, conventional SAW filters are on the way out, FBAR's coming in, and the leaders with FBAR are going to come in and push for tighter specifications and open up new opportunities. And it's, I keep coming back to this, it's a open, collaborative, competitive process with natural tension in the system to push to achieve the right balance between the different trade-offs. I personally think the standards process is serving us well.
Can you just add to that? I think I would agree with Bill. The comment I was making was more when there is bands overlap. We would try and maintain a single band.
You don't need to be defensive.
I certainly see that more and more bands are being released by the regulators, and these bands are coming to the standard, and we fully support that, because that's, we need the extra bands to provide the extra capability to support broadband services.
So let's build on that a minute and get back to a comment that Gene made about the limitations of the Qualcomm chipset being limited to 3 bands above 1 gigahertz and 2 below. And obviously, as the FCC is working very hard to release new spectrum for mobile broadband, so you know, in the future we're going to see a trend toward even more bands available and even more work for you guys in 3GPP. On top of that, you have Bill's comments that you know, the low frequency spectrum requires the components require more real estate inside the device. Very true statements, and that the device size is a big limitation from an operator's point of view. However, the way I see it, we're heading toward more spectrum, more bands. Gene, you'd mentioned that Qualcomm's working on expanding the capabilities of the chipset. We're also heading toward a world of potentially carrier aggregation, in which 2 receivers are going to be required inside the chipset. I'm sorry, inside the device, you know, which could free up some additional ports for additional bands. I'd like you to comment on that. But in other words, what I see is devices getting more and more complex as time goes on, and if you could predict the future, what's going to happen? How are we going to resolve this problem in terms of supporting all the bands that need to be supported in a device and doing it in a way that the operators are happy with the size and form factor of the device?
Yeah, I'll just add to Tom's question, specifically if you could address SDR, software-defined radio, where you see that coming into play anytime soon.
Okay, thanks for the questions. Let me try to address those questions. It's a real challenge, as you pointed out. These devices, you know, to support this technology these devices are incredibly complicated, as you might well imagine. And at least there's, if you take a look at just, you know, there are multiple dimensions to this problem. If you take a look at the just the time dimension, just because of the incredible complexity of the devices, to be able for Qualcomm, for example, to be able to put out a new chip, a new device, is an enormous amount of effort. And it's not that, as much as I'd like, it's not that I can crank out another chip next month or something like that. I mean, obviously, these are, you know, measured in years, not in weeks or months or anything like that. And that, you know, that brings quite a bit of challenge, because we need to define what their future products look like, you know, well in advance in order to be able to accommodate that. The other challenge that we have is that, you know, gosh, the number of bands that we see is just it's exploding, and it far outstrips, you know, what we feel as practical in terms of a device. I mean, I can't build a device that, you know, let's say that today I have 2 low-band ports and 3 high-band ports. Well, you know, should I build a device that has, you know, 4 and 6, or should it be 6 and 8? I mean, you know, it's a never-ending thing, and I'd never be able to keep up. And so clearly we need to address that somehow. And then the other dimension is that, you know, there's the practical, you know, reality. There's, you know, what Bill pointed out is that, you know, you're limited in size, right? I mean, there's only so many duplexers that I could put on a UE, you know, before we get to a tablet-sized product or something like that. And I guess, you know, nowadays the trend is to get to slightly bigger UEs because of the screen sizes and things like that. But I mean, still, we're fundamentally limited in, you know, other dimensions other than the number of ports that the particular chip can support. There's cost as well. You know, to be able to add another port to the chip obviously increases the silicon area, and the silicon area has a direct impact on the cost. And, you know, this is in addition to the external components that would be required to support this. So there's cost, complexity, there's time. So there's a number of these issues. You touched upon carrier aggregation, and I'm glad you did that. Carrier aggregation is an interesting, you know, new development that we're just actually starting to develop the specs for in 3GPP. And I feel that the initial deployments or the initial implementations of carrier aggregation basically are going to, as you alluded to, are going to use two discrete chips to implement that. And while that does give some opportunity, for example, to have more ports available, there are also some, what I think are going to be some challenges ahead in terms of just RF plumbing, for lack of a better word. I mean, we need to somehow be able to operate these 2 bands simultaneously. And so generally we're going to need some sort of diplexing device or something like that to be able to just plumb these devices. And that also adds to the complexity. Now on top of that, if we need to support more bands, we were talking about a pretty complex UE. Unfortunately, generally, complexity adds some nasty things associated with it, such as, insertion losses, which is noise figure and things like that. And so in some cases, we have to somehow figure out if we're going to be able to overcome or somehow deal with those obstacles as well. And lastly, Julie, you mentioned software-defined radio. Obviously, it's I think I was working on software-defined radio when I was in grad school. So, and that's been a while. So, it's been an area of research that's been ongoing for a long time. I think that there have been some improvements made. Obviously, the technology is improving and so forth. Unfortunately, I don't see it as a near-term solution that's going to for this particular problem. I think there are some unique problems that it may be more well suited for, but unfortunately, at least my perception is that for this problem may not be the near-term solution.
First of all, I agree with almost everything you mentioned. I do put out a couple of different topic areas with different comments. Number one is that if you're actually going to look at having a lot more bands in the future, and you're talking about this 35, 50x, whatever the number is that people believe is the number of network capacity is necessary. You're not getting that just by spectrum. You're getting that by a lot of spectral reuse, which means you're moving from a capacity. You're moving to a capacity build, not to a coverage build, which means the standards may need to change in some respects to actually adapt to that, because you're not having to throw many multiple kilometers. You're going into very, very few kilometers, especially in a lot of those areas. So it actually starts getting you to think a little differently, and maybe we need to start thinking a little differently about what this all means with the sense of our architectures and our standards to begin with. We built these standards for a good reason, because we only had 1 or 2 bands, and we needed to make sure we used them as best we could, and we basically made sure that the roll-offs were perfect and alike. When you start being able to flip bands and be able to actually change and adapt, which you're starting to see already. And we were talking about software-defined radios? No, not in the classic sense of graduate student days, and I taught some of those classes, of all this thing's going to change and do everything. However, you're doing software-defined radios now. You have network signaling that's going on and changing the parameters inside the devices as they go on. You're having the base stations doing automatic resource management to be able to balance out. You are seeing those things that are valuable to the network operators being built in right now. Handling interference, handling more capacity, handling more dynamics. Okay, it's happening today. But what I try to help people is think about what you really need. And just one aspect of this, what technologies that are out there, you have to think about, and the universities are doing this right now, and it's been published quite a bit, the ability now to think about tunable filters, which is where we're going to have to go eventually. If you're going to go with all these bands, I don't think you're going to have a 500-port device in the future. Eventually, you're going to have to look at a little bit of programmable filters. And those are happening in the academic era, and they're actually starting to work. I mean, it's been a long time. They're not all the way there yet, but I think that industry, I do know that some of the industry is actually being involved with them right now. So we have to actually state that for the regulators and for the community that this is going to be somewhere we're going to go, or else we're going to have to go there if we're actually going to have as many of these disparate bands. Or we go into a band aggregation where we actually clean slate it all, FCC come back out and reallocate and clean it all up, which I don't think is going to happen. Unless you think so, Julie.
Just to take on, because we have a question that was similar along those lines, that is, we're searching for the spectrum for 500 megahertz for wireless broadband. And we look through the spectrum and we're trying to identify bands where we can gain access to that, either through reallocations or sharing or something. These challenges only get harder. So I think, Paul, you kind of hit the nail on the head. We're going to need new ways to deal with these, otherwise the devices grow and the power drain, the insertion loss gets worse. Is there anything else that we ought to know about that's coming down the pike to help solve these problems? That's it. Paul's got the answers.
Ooh, I like that.
Yeah.
Thanks. Thanks for the comments, Paul. And I did want to make a couple of points to address that. Yeah, one of the points that Paul made was that this capacity versus coverage situation, and you know, we need to obviously consider both. And I do want to point out that we are considering such aspects in the standards. Some of these, for example, heterogeneous networks, are techniques that we can use to improve capacity and things like that. So these are things that we're looking in the standards. And then to the point about software-defined radios and tunable filters and things like that, I think that I also agree with Paul that there are many, how should I call it, adaptive techniques, network adaptive techniques that are being introduced and successfully used today. I guess I was thinking more in terms of flexible RF front ends and reprogrammable and retunable RF front ends. And that's where I think we're not quite there yet. The tunable filters idea, I mean, that's something that obviously I'm very excited about. I'm looking forward to with eager anticipation. But again, I also think we're not quite there yet. From what I've seen, the cues that we're able to achieve with such filters and things like that, we still have some work to do.
We'll talk offline.
Getting there.
But I do think it's important to note, and I think Paul and Gene are saying this, that innovation is taking place in the ecosystem. We're not necessarily, the vendors that are innovating aren't necessarily, a lot of them operate in stealth mode until they're ready to actually get into engineering samples or some condition where they're ready to demonstrate to the market. But I absolutely, I'm confined by NDAs and things of that nature, know that innovation is taking place within the ecosystem that's going to help us solve some of these issues. But the key is we're not there yet. It's coming, and it's happened many times before. You turn the clock back 20 years, the network capabilities, the device capabilities were radically different and inferior to where we are today, and we see that same path ahead of us continuing. So there's definitely innovation taking place.
I think we have time for one more question, and then I'll give everybody an opportunity to make some closing comments. This one comes from, I believe, someone in the audience. 700 megahertz band, lower and upper, was originally planned and designated almost 20 years ago, well before LTE technology was developed. Given the challenges to maximize utilization of the entire 700 megahertz band, what FCC actions could eliminate potential interference and maximize full use of the lower and upper 700 megahertz band? Gives examples such as elimination of Channel 51 licenses. I guess who's best to answer that one? Harmonize the power levels and uses of channels 55 and 56, and urge public safety to use 700 megahertz for mobile broadband only. Who wants to comment?
Yeah. Agree with that. Good answer.
Any other comments? Go ahead, Jim.
Thanks. I think that one of the key challenges in 700, actually in any band really, is interference, particularly when we talk about dissimilar services. Mm-hmm. So if you have dissimilar services that are adjacent or very close to one another, then one of the natural fallouts is interference. And to the extent that you can mitigate dissimilar systems, I think that you greatly improve the opportunities and the probability that you can get something that works well overall. And so I think the examples that were mentioned in that question are quite pertinent. I mean, for example, channel 55 and 56, it's broadcast technology, but as if we're able to convert that to something that's more similar to, the usage nearby. And what I'm saying here is, a cellular type usage, then that helps to mitigate the interference conditions, and that helps to provide more efficient use of the spectrum. So in general, I think my general statement is that to the extent that we can mitigate dissimilar services in the band, we improve the situation.
We had just one other question we didn't get to from the audience. This for the whole panel. There are still several high-powered transmissions in lower block E besides the media flow system, which does not allow a nationwide solution for band 12. Why do you assume these are going away?
I'm not sure that I can say with certainty they will go away. Directionally, that's the way things seem to be heading, so I guess it's a bit of a leap of faith and hope on our part, and back to the point that Gene just made, that any help we can get from the commission or elsewhere to mitigate dissimilar services, and that's certainly the big issue here that's creating the interference problem. So hopefully they will go away.
Could probably add a market note to that as well. If you think about the direction that appears to be heading with AT&T, both in the standard of supplemental downlink and their hopes of closing the acquisition of media flow spectrum. Those two factors would bring a significant market weight to the problem, such that if there are just a few holdouts, you would think that there would be some sort of a market solution, if not a commission approach to it.
Great. We're running to the end of our time. Wanted to give everybody the opportunity to make some closing comments. We've touched on several issues, but this is a multifaceted discussion that we're having, and if there's anything that we happen to not touch on that you'd like to point out and elaborate on, please take a couple minutes to do so. Let's start with Edgar at the end.
I don't think, as I said in my presentation, we didn't really cover the challenges of band 13 and band 14, so I really want to try and address that particular aspect. So certainly we would strongly support combining 13 and 14, but we see there's significant technical challenges, and this will certainly impact existing band 13 devices and public safety broadband. So I want to just run through these issues now. First of all, changing the duplex bandwidth from 10 to 20 and reducing the duplex gap from 20 to 10 will increase the insertion loss filters. That's without a doubt. So we'll see a 1 dB hit in terms of performance, and that's the best case, probably be more. We've seen inputs from filter vendors showing much higher numbers than that. So there'll be 1 dB hit for that. But the other issue that's that's been missed so far is that you can't, once you go to these sort of duplex gap ratios, and if you look at the LTE specification, you notice that we have, for some of these bands, such as band 2 and band 8, which have been identified as wideband CDMA bands, you actually have to reduce the power for the edge channel allocations. As I mentioned, it's a narrowband system, LTE. So if your edge transmission band, for example, wideband CDMA is 2.4 megahertz, your resource block allocation at the edge, they will have to be reduced by approximately 1.5 dBs. LTE, the control channels are sent on the edge, so your control channel power will have to be reduced for band 13 and public safety broadband. D block will be ineffective because it's in the middle of the band. So that's a big issue with combining that area. The other area is duplex filter impacts on public safety coexistence. I think that it's quite rightly pointed out that you're now in the emission mask, and therefore the duplex filter doesn't really help. But that's not strictly true. As we saw in band 12 discussions, there were filter vendors promoting 0 ppm filter technology. 0 ppm filter technology will allow you to have transition bands of around 2-3 megahertz. Once you've got that sort of transition bands, you can certainly provide significant protection for public safety narrowband, which currently is not capable of doing it. And what we have to do is find some signaling methods where we actually tighten the emission requirements for band 13. Currently, band 13 devices not only have to meet FCC requirements of -35, they also have to meet -57 dB requirements. That's 21 dBs tighter than FCC requirements, purely to address coexistence with public safety narrowband. And that was not identified in any of the discussion papers. So then the other aspect also mentioned was GPS. Now, I think we saw some slides showing the impact of GPS, and you could put a notch in the duplex filter. But I think you also may need to consider that SAW filters and even FBAR filters are not linear devices. So you can't actually use the filter to attenuate the GPS frequency. You need to put an additional filter up after the duplex filter, and even possibly after the antenna switch. So and these notch filters add about ½ dB insertion loss. So that makes your design very complicated when you want to support multiband devices, because this notch filter has to be not after the PA, not after the duplex filter, but possibly after the antenna switch, unless you use very expensive antenna switches. So mixing band 13 with other devices significantly impacts the complexity of the corresponding devices. And the third issue that perhaps people have not taken on board is we're really moving to cases where we're doing simultaneous uplink. And we currently see that in devices already in the market, where we have CDMA and band 13 devices simultaneous. So you now have intermods between these two uplink transmitters. Increasing the passband from 10 to 20 is certainly going to be a problem. And if you say, well, maybe in the future we will not need that approach. You may need that for carrier aggregation. Same problem arises. So yes, 13 and 14 is desirable, but it's extremely onerous at the moment, and you certainly increase the complexity and cost of devices once you start to mandate that sort of requirement. And that's something that I think people need to take on board, that basically, because band 13 is probably the most complex band in the 3GPP standard. I don't know if anybody would agree.
Paul, closing comments?
Okay, I'll just make mine very, very brief. I think that it's both a technical issue. I'm talking about interoperability. That's why we're here today. And it's both a technical and a business issue. That's why you're actually breaking us up into two sessions. But I think they're so intertwined, you have to start asking the questions that we're talking about here and how they impact the business decisions. Meaning, before, again, interoperability is based for an aggregation point. It provides an ecosystem and an aggregation. And that also is a business decision if you actually want that aggregation. The technology is available, I think, in a lot of ways, depending upon if you have multiple bands, you can deal with interference in a lot of ways. There's a lot of technology, and agreed that there are some challenges associated with that. But overarching is that it's a business decision to balance out those extra costs and those issues associated with the ability to provide that type of ecosystem. And I think we need to take a look at that very carefully as a nation and as a regulatory agency.
Thanks. Bill?
I think I would just echo Paul's remarks. I think we have to balance the business and technical issues. I think I would side more on the technology is emerging side of the argument. Definitely, as I said before, innovation is taking place. I think some of the cost and complexity and size issues make it very difficult when you consider the trade-offs. And at the end of the day, we have to keep the customer in mind and make sure whatever it is we're doing here is aimed at satisfying or meeting the requirements of the end user.
Doug?
So I'd like to respectfully disagree with Edgar on a couple of points. One being the state of filter performance. 1 dB seems a bit high from some of the filters I was looking at. It seemed like significantly less insertion loss was feasible. Also, respect to the public safety narrowband interference, the curves that I was seeing, being 2 megahertz away, it's very difficult to get a filter roll-off that significantly helps over the entire PSMB band. And so we do look to the emissions mask to meet the FCC protection criteria for public safety narrowband. And then in terms of the GPS issue, what is most important to my mind is whether there's an active transmission within that 1 megahertz block. If you look at the frequency spacing of the upper C block carrier, the D block carrier, and then if you consider the possibility of a wider D and public safety broadband carrier as well, there's not that much of a spectral separation between those 3 cases. And they're close enough to either band 13 or 14, filtering. The primary duplexer filter is not going to help with that roll-off significantly.
Thanks. Gene?
You know, we could talk all day if you let us, so I won't do that. I think in closing, what I want to say is that, I think that at least I can speak for my company, and we're motivated to try to support as many bands as we can. And to provide as much capability as we can in our chipsets. Obviously, we want to sell more chips. But there are some serious technical challenges that need to be overcome, and if there weren't, we wouldn't have this discussion today. And I think that we're all recognizing that. I think that we could go a long ways to addressing some of the interference conditions. I think one of the principles that I mentioned was to the effect that we can mitigate dissimilar services within the same band. I think that really helps the interference conditions, and that helps to alleviate a lot of the problems that we're faced with. But these are some pretty serious technical challenges, and I'm hoping that we can move forward. Thanks.
Great. Well, wanted to thank all of our panelists for coming. We'll take a short break and meet back here at 10:45 for the second panel. Let's give our panelists a round of applause. Thank you.
If we could try to get started for the next panel, please.
Unfortunately, I didn't bring any of mine.
Thank you, and welcome back to the workshop. Just a couple of reminders for those of you who may have joined us late. We are streaming this live on the web. Those of you who are watching the live stream can submit questions for the panels by submitting an email to livequestions@fcc.gov, and please include your name and the organization that you're affiliated with in your email. And those of you here, we have note cards and pens. If you do have questions, please feel free to submit the questions, and Michael or myself will just be walking around. Just raise it up in the air and let us know you have a question. Also, we got a question during the break. The archived webcast that we're streaming will be available on the FCC events page along with the presentations. And the presentations will also be submitted into the docket under rulemaking number 11592 in ECFS after the presentation. That may take a day or two, but they will be submitted into ECFS also for those of you who want the presentations that were given today. So now we're getting ready to start the second panel. The moderators for this panel will be Jim Schlichting, who is the Senior Deputy Chief in the Wireless Telecommunications Bureau, and will be co-moderated by Tom Peters again. Thank you.
After the first panel, I guess I'd say I would definitely would have felt an interloper amongst all that technical discussion, and I want to thank Tom to have a second panel that focused on some of the non-technical issues, the market issues involved in these interoperability debates and discussions and the like. But the technical challenges aren't totally far from some of the market issues as well. So Tom has gratefully agreed to co-moderate the panel, and we have a fine set of panelists to deal with what are the market issues. So that the first panel tried to focus on specific technical and standards issues, but actually getting product to market and having consumers having choices and having 700 megahertz equipment available also is affected by market issues in terms of availability of devices, availability of components at competitive cost to all sorts of providers and the like. So without further ado, I will sort of introduce the panelists we have to focus on the market issues. First, on the left side of the panel in front of us is Stacy Black, who's Assistant Vice President for Market Development at AT&T. He's responsible for product management for advanced mobility solutions for enterprise and government segments. Particularly his interest oversees products and development that include 700 megahertz public safety LTE managed services, next generation packet switch and priority services, and next generation push to talk over IP services. So we're going to be bringing a small bit of what's a much larger debate on public safety interoperability. That is the device side of it to the discussion on this panel. Next to Stacy, we have Michael Chard, who's Senior Director Business Development, Qualcomm CDMA Technologies. He develops business for Qualcomm CDMA technologies, working with numerous service providers, including those who own lower A block, 700 megahertz A block spectrum, as well as many device manufacturers. Oh, they do. No, I'm sorry, they have them in a different order. I apologize. Sitting between Stacy and Michael is Eric Graham, Vice President, Strategic and Government Relations at Cellular South. Eric serves as Vice President for Strategic Relations, Mississippi native, responsible for developing business and policy solutions to achieve Cellular South strategic goals, and responsible for the company's overall advocacy efforts. Then I need to check. Okay, Matt Wood is next, who's Associate Director at the Media Access Project, where he's worked since 2009. Works on a wide range of topics, including universal service, broadband deployment, broadband adoption. Media Access Project, along with a number of other public interest groups, have been very active in this proceeding, and we're very happy that he was willing to join us. And then at the far end of the panel is Dennis Martinez, who's Chief Technology Officer, Harris RF Communications Division of Harris Corporation. Harris RF Communications is a leading global supplier of secure radio communications and embedded high-grade encryption solutions for military, government, and commercial organizations. Dr. Martinez has worked in the development of advanced telecommunications and product systems serving mission-critical markets, including national defense, public safety. So again, we have somebody who's able to deal with some of the public safety interoperability issues on the device side. So again, thanks to all the panelists for making the time to come visit with us this morning. And with that, I'll turn it over to Stacy.
Thank you. And good morning with everybody. AT&T's customers really aren't interested in bands or the number of bands inside of a device. They're really just interested in high-performing, affordable devices that work everywhere. When we look to develop devices, we look at the following factors: cost, form factor, size, performance and speeds, and backwards compatibility. This was the basis of our ex parte comments last year, where we identified 4 areas that directly impact these goals. First, the proposal that was put forward last year would delay 4G rollout. AT&T is trialing, and Verizon has already rolled out, devices and networks that will use blocks B and C respectively. And changing the band, this plan would force us and our partners, our manufacturing partners, to start over and switch to new bands, which would require substantial and additional development, testing, and trials. Number 2, it would slow consumer adoption of 4G. Modern chipsets, as was already pointed out in the earlier panel, can only support 2 bands under 1 gigahertz for broadband. Forcing carriers to incorporate 2 4G bands into all 700 megahertz devices would foreclose backward compatibility with legacy mobile broadband networks. Forcing carriers to use devices that devote both chipset bands to 700 megahertz would mean that devices would work only where where LTE service has been deployed, and given that it will take years to achieve ubiquitous coverage in LTE networks, consumers would be reluctant to purchase LTE devices that only work in a few places. Number 3, it would increase the cost of 4G networks and prices consumers pay for 4G services and reduce the quality of services. To even partially address the significant interference caused by this proposed band plan, carriers would be forced to deploy extra base stations, increasing costs and delay, and even then, base stations and devices would be subject to additional interference, causing lower quality, coverage gaps, dropped calls, and higher cost services. Number 4, it would severely impact the Commission's public safety goals. All of these problems, delayed deployment, lack of backwards compatibility, increased cost, costlier and less feature-rich 4G devices, would have significant impacts on public safety, which would frustrate the Commission's goals for the deployment of nationwide interoperable public safety network. We also identified a 5th issue, and that's that you just can't change the band plan after an auction. AT&T does a lot of due diligence before purchasing spectrum, and in this case, The Commission and the standard-setting process made it clear before the auction that the A-block spectrum posed particular difficulties with respect to interference, and those difficulties are fully reflected in the fact that the A-block group carriers won licenses in that spectrum at considerably lower winning bids. It would be patently arbitrary if the Commission were to pull a bait-and-switch on the industry now, radically altering the band plan upon which the auction was based and reducing the value of B and C block licenses. That's all.
Eric? Good morning, and thank you for letting me be part of this esteemed panel. Cellular South appreciates the opportunity to be here to discuss some of these issues surrounding the business obstacles to deploying LTE, given the current band plans and, frankly, given the available scale to a lot of the Band 12 operators who are out there. At Cellular South, my role is somewhat multifaceted, and I have the somewhat unique standpoint of being able to speak about our spectrum acquisition efforts at 700, our LTE network equipment and device procurement efforts, as well as our ongoing efforts to try to mitigate the harms that have been put in place by some of the band plan changes since the auction. I would agree with my colleague Stacy Black that you can't go in and change band plan after the auction, but after the auction, that's exactly what potential Band 12 operators, lower A, B, and C licensees found themselves in the situation of facing. The auction, as you know, began in early 2008, closed in April of 2008, and just a couple of months later, roughly June of 2008, a proposal was introduced at 3GPP that would have taken the existing, and did in fact take the existing Band 12, which was there for lower A, B, and C blocks, and carved out a subset of that, the lower B and lower C blocks. Since that time, development proceeded at a rapid pace for Band 17 and stagnated for Band 12. We were put in a unique position in the 700 megahertz auction because there were multiple bands that we had to deal with. If you travel with me back to 1981, the FCC put forth a requirement that with the initial cellular licenses, there would be one band, and any device built for the A license of cellular would work on the B license for cellular and vice versa. Moving forward to the PCS days, there was a single band class, no FCC requirement at that point, but certainly not the unprecedented market concentration that we have in the industry today either. And due to the vast number of competitors and their relative sizes at that point, there was one band class for PCS, maybe multiple air interface technologies, but one band class, and therefore any device that worked on, for example, the A block of PCS worked on the B, C, D, E, F blocks of PCS, and vice versa. AWS saw the same thing for the AWS spectrum that has been auctioned to date, but then you enter the world of 700, and suddenly we come to find the world has changed. Changed because due to significant market concentration, scale is everything in this business, and those with the scale chose to promote and develop and procure devices and equipment for only specific portions of that 700 megahertz space. What that did for the rest of us, particularly in the lower A, B, and C spectrum in 700, was force us into a new world of trying to source devices that would be built for a much smaller scale than we had ever seen before in the history of the industry. As we went to device manufacturers, the device manufacturers would tell us the chipset's not there yet, go talk to the chipset vendors. We'd go talk to the chipset vendors, and the chipset vendors would tell us, sure, we can do it, but you don't quite have the scale to make this an interesting business case for us. Some of that has changed in recent months, fortunately. Device manufacturers, at least those who would be backwards compatible to CDMA, have a preference in their chipset vendor. And we have seen some recent progress from chipset vendors in that regard. We have had oral commitments, still hope to have written commitments soon on when some of these chipsets would be supported. Initially, it'll be a dual chipset solution. We'll talk about that more, I'm certain, in questions and answers. But the bottom line is, if you're a Band 12 operator you are faced with a significant scale disadvantage, which you potentially late to market in sourcing devices, sourcing network equipment, and rolling out your LTE deployment. And we've been fortunate in that we found a partner in Samsung who could provide chipsets, devices, and network equipment. But operators smaller than us don't have the advantage that we had, to the extent our minimal scale is an advantage, of securing this type of an arrangement. At the conclusion of the previous panel, the technical panel boiled down to the basic point that interoperability is an aggregation point for aggregating scale and driving ecosystems. You never heard that panel say that it was impossible. You only heard complex, difficult, but never impossible. If this was easy, all of us in the Band 12 would have done it in-house. It's not. It's going to take some work, but any technological advance does. You never heard the technological panel say it was impossible. Now it's time to talk about the business and the policy reasons for doing this, to speed deployment of LTE to the farthest regions of the country and to serve all consumers, not just those who live in highly densely populated metropolitan areas.
Michael? Let's see, we'll get the, great. Jim, thank you very much for the introduction, and we certainly appreciate the Commission inviting Qualcomm to be on the panel today. Just to add to the introduction, to give you a little bit of background in terms of the work that I do in QCT, Qualcomm Technologies, our chipset division. I work on the carrier relations side, which means that my day-to-day existence means working with the carriers, understanding their demand, and helping drive their requirements and demands internally with product and engineering inside of Qualcomm. Qualcomm has just celebrated its 25th anniversary, and Qualcomm ideas and inventions have been driving the evolution of wireless communications for a long time. We play a key role in the ecosystem, especially with many of the CDMA carriers, in terms of supporting them and offering them multi-mode and multi-band devices. Our chips exist in a wide variety of products, from tablets all the way down to low-end phones, high-end phones, and as we're currently seeing the smartphones that are entering into the market very rapidly. We've been driving the improvement of our chipsets and the capability year after year, whereas today we see devices that are more powerful and exceed the processing capacity that we had in PCs just a few years ago. So the rate of innovation just continues to accelerate. One of the key focuses in the areas that Qualcomm really plays in is supporting the multi-band, multi-mode chipsets to go into the devices required to be backwards compatible to support 3G technologies and 4G technologies as we roll out. A significant part of the work that we do is plowing a lot of our money back into research and development. Cumulative to date, we have invested more than $15 billion into R&D to support the industry and to provide the ecosystem with the chipsets and devices that are needed. Now, specifically, we're here today to discuss our support for Band 12 and for the rollout of the next 4G generations. One of the critical pieces is that all of the chips that we make that support LTE, 3G, 2G, also have to support multiple bands, including cellular, PCS, AWS, and the multiple bands within the 700 megahertz spectrum. We have chips currently available, and I'm going to talk a little bit about what we have from a commercial perspective on commercial availability and timing of our slides to enable the carriers, some of whom are represented in this audience. So currently, the commercial approach that we have is with our MDM 9600, and the MDM is the mobile data modem, which supports data devices. This is a chipset that's currently available commercially in the marketplace today. One of the challenges that we have, especially with LTE, is all the permutations on bands and bandwidths that we need to provide RF drivers for and do all of the associated testing, which is very labor-intensive, time-intensive, and so forth. Behind me are thousands of engineers that drive these products and do the testing. As we've been working closely with the Band 12 carriers, they have invested millions of dollars in acquiring the spectrum, and it's certainly in our best interest to be able to support them, provide them with the chipsets that they need in a timely manner. So currently what I'm showing up here on the display is the commercial availability of our MDM 9600. And talking about the multiple modes that this supports, including the 3G technologies, DO Rev 0, DO Rev A, Rev B, 1X Advanced, HSPA, HSPA Plus, and so forth. So you can see the complexities here. The critical element, as we look at this chart, is what we have committed to the carriers is that we would have commercial samples of our MDM 9600 deliverable in the September timeframe of this year. So generally what that means is when we supply commercial samples to their OEMs, they then are able to go out and order commercial devices several months later. We are not a handset supplier, but we do enable the infrastructure, or excuse me, the chipsets, and in this case we will be enabling the devices that will specifically be able to support Band 12. On my closing slide here, I just want to give you an idea of the complexities, involved in developing these chips, the modes that they support, the multiple bands that they support, the bandwidths that they support. But the critical element here is that we have made a commitment to deliver commercial chipsets with the MDM 9600 that will support Band 12, lower A, B, and C in the September timeframe of this year. Thank you very much. Thank you. Matt, before you, I noticed, I think Commissioner Clyburn came into the audience. Just wanted to acknowledge Commissioner Clyburn and dealing with the Commission staff has expressed great interest in this proceeding and in the petition on interoperability. So I just wanted to notice for the audience that she had come down to listen to part of it. So Matt, if you want to.
Sure. Thank you very much, Jim and Tom and Commissioner Clyburn and everyone else here. As the ninth speaker here at the tail end of the second panel of the day, there's not very much I can tell you, especially about the technical issues that you were briefed on so well in that first panel. So I'll just spend a few minutes, perhaps when we get to questions and answers, answering some of the other points raised by their speakers here, but also outlining why a public interest organization or a consumer advocacy organization like Media Access Project is interested in something as technical as 700 megahertz interoperability. Media Access Project is a 39-year-old public interest law firm that takes very seriously its mission to promote affordable access to open technologies and promoting people's access not only to receive content but also to produce content. Media Access Project has a history of working on broadcast matters, but has been working on telecommunications and internet matters now for the last 10 or 15 years at least. And we really see this as an extension of the First Amendment-driven mission of the Commission to promote expression and to promote people's ability to make use of these great devices that we're talking about today, not only to receive information, to download entertainment content, but also to express themselves in this online world into which we're transitioning. Access to wireless devices and services then are important because of the impact that they have on people's pocketbooks, but also because of the uses that people make of them for all sorts of economic and civic engagement opportunities, educational opportunities, and so that's why a firm like Media Access Project is as interested in this topic as we are. So just a couple very high-level points as to why we think this is important, and really playing off of some of the things that Eric said and that Paul mentioned in the first panel. Yes, there are costs from regulation and from standard setting. We've heard that many times today in very articulate terms, and another for perhaps a little higher pitch as to the cost that regulation imposes. But so too does lack of regulation impose a cost. And what we're talking about here is the ability of large dominant firms at some times to impose costs on their competitors, to raise the cost that their competitors have for equipment acquisition and deployment cost, and then ultimately for the price that consumers pay for those devices. So when we do have a situation where a firm can change the rules of the game in midstream, as we've heard bandied back and forth this morning, and to change the deployment timeline for equipment, it's not just a matter of one carrier's deployment being slowed, it's a matter of deploying equipment at a more reasonable pace for all competitive providers and giving people a chance to choose amongst different carriers. There are consumer reports, studies on this point released earlier this month that suggested that people do want to take their phone with them when they switch to a different carrier. Of course, there are all sorts of technical issues that play into that. People's ability to move from one carrier to another is determined not only by the device, but also by the control that the wireless carrier exercises over the customer choice. And so when we hear about providing consumers what they want, sure, carriers will provide consumers with what they want, but only if that makes them more money, if that increases the revenue that the large carriers can provide, and carriers who can reduce churn essentially by using tools like handset exclusivity and now by using tools such as technical interoperability limitations can prevent customers from moving to a different platform and from obtaining better service from a different provider. So that is the reason that we're concerned about these issues and why we think of interoperability as a challenge that has to be solved. As Eric said, it's not something that's impossible. There are different costs and different balances that have to be struck, and we feel that resolving these issues will ultimately benefit the consumer. If it raises costs at one point in the process, it will reduce costs overall and prices paid by consumers in the long run if they do have an option to take their phone to a different carrier, if their phone isn't limited to working on one single band class or subclass in a balkanized 700 megahertz world, and if they're able to experience savings by going to a competitive provider such as a Cellular South, such as all the different carriers we heard about in the first panel, in addition to the AT&Ts and Verizons of the world and the companies that have the scale to develop their own subclasses, as it were, and to have a device that only works on the spectrum in which they're licensed, which has not been the case we've seen in other bands. That is a new feature here in 700 megahertz and something that we think is harming consumers ultimately as they're forced to stick with a carrier and are not able to take their device with them or to purchase a device that will work on more than one carrier's platform. So, thank you.
Thank you. Dennis?
Well, thank you. Let me first thank the Commission for recognizing public safety as part of this ecosystem that's developing. You know, it's a rather interesting time because we have now for the first time a carrier that's not a commercial entity, let alone a single entity. It's a very amorphic entity, and it is a very unique situation we face today. Let me start by saying, do we have the charts? Let me start by saying that public safety is embarking in an evolutionary process. Today's communications public safety is bifurcated. We provide for mission-critical voice services today with dedicated narrowband systems, otherwise known as LMR or land mobile radio. Recognizing the limitations of that technology, public safety today makes extensive use of commercial cellular networks for data services. So today's common usage model for public safety is narrowband dedicated systems for their voice and commercial carriers for data services. On the far right, we see the end game here where we will have a nationwide broadband network built on LTE technology, a dedicated network for public safety. That network will provide all the benefits of convergence or voice and data services, nationwide services or roaming. It will be built to public safety grade standards, and it will operate with relevant technologies. Then we have this period in the middle, which is the period we're now entering into, where there's going to be a long transition phase from a very disparate environment to this one unique LTE network. And in that transition, there are going to be two kinds of interoperability that are going to be necessary. One is interoperating with existing legacy voice systems, and the other is interoperability with commercial cellular systems. So you can see from the very beginning that the situation in public safety is there's going to be the need to roam across commercial networks that are in use today and the LTE network for public safety that will be rolled out incrementally. So the roaming problem is there day one for public safety. So let's kind of look at what the key issues then we face in public safety. First is that there are, as we said, two technology migrations, one from narrowband voice and the other for cellular data services. It's interesting to note that migration and interoperability are really interwoven concepts in this migration process. Migration really is interoperation with legacy systems, be it voice systems or be it cellular data systems. The emergence of an all LTE environment in 700 megahertz presents an interesting scenario where we will need to interoperate perhaps across different LTE bands. Again, given that public safety already makes use of commercial cellular, that trend will not be eliminated anytime soon. We have a very complex emerging framework that's coming into play. There's a governance structure and an architectural issue that's being discussed. We have a third report and order that has already codified LTE as the standard. There's ongoing rulemaking with the fourth further notice of proposed rulemaking, and current public policy issues with respect to the fate of the D block, whether or not the D block will remain an independent auctioned piece of spectrum or whether it will be aggregated in total for band 14 for public safety. Public safety will have emerging business models, and we'll talk about that in a moment, and the Commission recognized this in the development of the National Broadband Plan. And finally, it's important to note that public safety is not a commercial business. It's a collection of mission-oriented enterprises whose job is to protect life and property. The service levels, coverage, capacity, et cetera, are not based on commercial values. They're based on the mission of public safety. The challenge and opportunity that we have today is to leverage this commercial technology while maintaining that mission focus. With respect to the business model, the Commission anticipated that multiple business models would be contemplated by the public safety community. On the far left is the dedicated network, the traditional business model where a jurisdiction builds, owns, and operates a network. And the far right is a fully service-oriented architecture, purely commercial retail services, and then a whole world in between. Early procurement activities by public safety suggest that indeed all models are currently being contemplated, and that will further complicate the issues of deploying the network and managing the roaming across the public safety network and the commercial networks. Let me end by saying that the market itself is very non-monolithic. We have a diverse governance structure of states and cities and counties, tribal and federal government organizations. The needs vary across large states, across cities and rural areas. The mission requirements themselves are different between first responders do law enforcement versus fire service, for example, and the funding mechanisms are extremely complex. So added on top of the whole complexity is the fact that now we have a very complex funding structure in the build-out and deployment of this network. Traditionally, the public safety market has deployed new technologies very slowly. That's about to change. And with that change, of course, is the challenge of how do we maintain that network in synchrony with a rather rapid, by comparison, evolution of commercial technology. So exciting times for us, to say the least. Thank you.
Thank you very much. Appreciate, again, the work and the presentation of all the panelists. I think that at this point, sort of start with follow-up questions. Eric, I guess I wanted to start to allow you an opportunity to build on. You made mention to the dual chipset option and movement. So if you could sort of expand a little bit on sort of where you guys are now and where you think, from your perspective, you see the technologies and devices moving in the future, building on what you said during your presentation.
Sure. The first generation of LTE devices, given that LTE is initially a data upgrade for most carriers, include a legacy chipset that reaches back to CDMA or GSM, as well as a paired LTE chipset that will handle the LTE data sessions there. That is a chipset that, for one of the leading chipset manufacturers, is not available yet for Band 12, but will be available in commercial samples in September of this year. That's important because as we deal with device manufacturers, there's a comfort level there and a willingness to take those chipsets and not quite take them, plug them in, and sell the phones, but they know the chipset will work. There's a confidence level there. That's important. And that's a chipset availability that won't be available at Band 12, as I said, until we understand September of this year. That's a capability that has been available at Band 13, and I can't speak to Band 12, perhaps Mr. Black can, but our understanding is Band 12 for many months now. And devices that are coming online now for Band 13 have this dual chipset availability already. The next phase of that is to take the dual chipset solution and bring it to a single chipset solution. You heard Michael mention the 9600 chipset, which is the dual solution. The 8960 would be the single chipset solution. And as yet, we have no date for commercial sampling of the 8960 for Band 12. Important because, as the first panel discussed, as we've heard here, form factor is important on these devices. And when you can get to a single chipset solution, you get to a much better form factor to serve the customer. Ultimately, the customer wants sleeker, slimmer, more capable devices. The single chipset does that. Without interoperability, without required interoperability, you'll continue to see this lag for Band 12 versus the other band classes at LTE and 700.
Michael, can you shed any light on what you see sort of on a going forward basis with regard to new chipsets beyond September?
Absolutely. I would like to address the point in terms of timing. Eric brought up the point of timing on support for Band 12. As I mentioned earlier in my presentation, the MDM 9600 is commercially available today and is deployed commercially in the marketplace. A lot of that is due to carriers using other bands having timing advantages based on when they acquired spectrum and so forth, and working with us very early on. All of the Band 12 carriers have been working with us for some time. There were some significant technical challenges that has already been discussed, or have already been discussed in the previous panel. That we went back with our RF system engineering and came up with a solution to help alleviate and mitigate those problems. So that's where we ended up with the timing for Band 12 on the 9600 now. Now, a key part of that as well is the fact that we are supporting multiple bands to support both LTE deployments in bands 2, 4, 5 as well, because as most of us know in the wireless industry, it takes many years for people to deploy, for carriers to deploy coverage nationwide. So until we get the nationwide deployment of LTE, we have to be able to support all of the other bands. Now, Eric specifically mentioned the 8960. The 8960 is probably the most complex chip that Qualcomm is working on building today. We have publicly said that that'll be a chip that will have commercial samples available at the end of this year. Now, when we roll out commercial samples, we also have to roll out the associated band support with that. That's a little bit too far out of our horizon to provide specific schedules for Band 12 as well as schedules for other bands as well. But it's certainly our intention to support Band 12. It's in our interest to enable the ecosystem to provide as many chipsets as we can, and we know that's of vital importance to the carriers, and that's certainly our plan to move forward. But we have not put out schedules on that yet.
Thank you. I appreciate that. With regard to the sort of on the public safety challenges that Dennis addressed with regard to are there on the device side, are there any things as you're having to deal with, or the issues in the Band 13 and 14? Well, let me rephrase the question. In the prior panel, there was the discussion at the very end by Edgar Martinez on the question of the aggregation of 13 and 14 and some of the challenges. How does that fit into how you're looking at the public safety interoperability issue? Is that a key element of going forward, or are there other issues that you think are more important?
Well, the first issue to resolve is the D block. So the question here is whether the D block will be part of the public safety spectrum allocation or not. If it is not, then we have an interesting technical challenge in that now we have adjacent to D block operator to public safety operators. And there have been ex parte filings on this matter. That is a significant challenge from an interference perspective. Now you have this one isolated band, which is sort of half of Band 14, the public safety band. So the first and foremost issue to resolve is the D block. Once resolved, okay, now we have the issue of how do we ensure protection of both the D block, or I should say Band 14, Band 13, and on the other side of Band 14 is the public safety narrowband spectrum. So I would say it's sort of, I would echo the comments Edgar made earlier that I would say Band 13 and Band 14 represent sort of a unique set of challenges. On the upper side of Band 14, given you have the narrowband side of public safety, you have a very different technology. And a point that was made earlier today was that dissimilar technologies are much more difficult to address interference issues. So here you have narrowband and broadband as adjacent to each other, so that's going to require particular attention. We believe co-location is an important strategy to be used. We believe that initially public safety organizations are going to be inclined to co-locate with their own existing systems when they have, which are in place today, but the need to co-locate with carrier operators will inevitably happen as well.
One of the things about a public safety device is and we've had multiple panelists talk about on the commercial side the sleekness and the form factor elements with regard to those devices and how critical that is in the marketplace. Obviously, the traditional public safety device is a little bit larger, so to speak. In some respects, does that provide sort of more of an opportunity on the public safety side to deal with some of these multi-band issues that were being raised and the technical challenges? I mean, to the extent you're...
It does. And the other thing that's good is that initially, early usage will be primarily data-driven and not necessarily in a smartphone form factor. So early form factors are going to be conducive to the challenges that we're going to have relative to RF, managing RF interference. But as time goes on, the interest in public safety is to move more towards a smartphone-like device, small device. Because of the scale of band 14 relative to other bands, invariably we expect them to cost a bit more, but still rather competitive compared to today's narrowband technologies.
Are there particular components and achieving economies of scale that might be most critical to it? Because you're not going to have the scale in the ultimate devices, but maybe there are key components that would be part of commercial devices and part of public safety devices.
Right. So certainly the baseband all scales perfectly with the ecosystem. It's really the RF components that make up duplexing and the filter structure that's on the RF side of the baseband processing. So that's going to drive, to some degree, form factor and cost structures.
Is there anything?
I have a question from the audience, which is, I'll read aloud here. It appears that with a few minor adjustments to technical 3GPP requirements, interoperability is possible now, per the first panel. All consumers are interested in competition, price, availability of handsets, and coverage. Interoperability will provide more networks, better coverage in more places. Anyway, can't read that. So the question seems to be for AT&T. Does AT&T prefer slower 4G rollout for your customers, dropped calls where there is no coverage, or are you supportive of interoperability to improve the consumer experience, moving to 3G and 4G?
Well, if I understand the question correctly, I think I addressed it in my opening comments. I mean, AT&T is concerned about cost, form factor, coverage, and of course that coverage element has a backward compatibility element that is critical. So every device that we have developed is always backwards compatible to our 3G and 2G networks, and that gives our customers the greatest possible coverage area. And that's really what it's all about, and we try to do that at the best possible price, the best possible form factor.
Let me just add, I know there's certainly a great deal of interest in being able to support multiple 700 megahertz bands in a single device, and certainly in an ideal world, that's what we're in the business to enable. Currently, I think has been discussed a little bit from the chipset perspective, and in this case, we're talking about RF chips, which in our parlance is the RTR 8600. We also have the baseband chip, but currently it's not technically feasible to support multiple bands of 700 in the same device. So we have that technical challenge that we can't do. Now, that's not to say that that we certainly wouldn't want to go in that direction. That makes all the sense in the world if we could do that, but that's a technical impediment that we currently have.
I just want to reach back to something I said a few minutes ago, and something that you did not hear from panel one, nor did you hear it from Michael just now. He said technical feasibility, not technical impossibility. As we've done some of our outreach to various vendors, some of the things we hear back from vendors who talk to other vendors are, had the initial orders for 700 megahertz equipment required interoperability, we would have interoperability today. It wasn't a matter of technical impossibility, it was a matter of the course that was chosen initially in device procurement. So again, we won't hear that it's technically impossible to do this. We'll hear that it's difficult. We'll hear the feasibility question, which again gets back to what panel one reached at the end, which is the balance of business versus technology and what can and cannot be done. Obviously, cost is the driver of that. And there are a number of costs out there, a couple of costs that consumers pay with a lack of interoperability, is lack of competition because of a slower rollout for non-band 13 or non-band 17 devices. Consumers face the cost of a new device, switching carriers when devices are not interoperable. Consumers pay the cost of public safety not having interoperable devices, particularly in areas where this eventual public safety network does not extend. I could tell you stories about Hurricane Katrina and first responders having to get cellular South phones because the public safety network was down. Interoperability provides access to multiple redundant LTE networks when that device can hit any available network. In a lot of areas, it could provide the first network available for first responders. Where I come from, I can drive less than 15 minutes from my house and on a given Saturday afternoon go through an intersection where volunteer firefighters are standing there with their boots taking donations to get the equipment that they need. Interoperability for public safety can bring the devices down, according to CRS, $2,500 from roughly $3,000 to roughly $500, which puts technology that would be available to the DC Fire Department in the hands of the Pelahatchie Volunteer Fire Department back in Rankin County, Mississippi. Or technology that's available to the NYPD could be available to rural sheriff's departments anywhere in the country. And then another cost that a lack of interoperability has is a cost to the government, which is a lack of interoperability and a lack of a certain ecosystem will affect the bidders in the next auction. If we went into the next auction without the certainty of interoperability and the certainty of an ecosystem at the conclusion of the auction, we would be fools. We would be fools. We don't have the scale to drive an ecosystem, notwithstanding the minimal progress that Cellular South has made in that regard. We would be fools to go to another auction without interoperability, certainly without having recouped the investment that we made, $192 million in licenses in the 700 megahertz auction.
If I could just respond to that. So, certainly, agree to Eric's point that interoperability is an ideal situation to have. That's certainly a direction that we would strive towards. One of the complications, as I mentioned, is the RF chip. Generally, the development on that is about 3 years. So we're on our current generation, the RTR 8600 right now, which, as I mentioned, does not support multiple bands within 700. Now, as I showed in my chart, it does support all of the, many of the other bands to allow coverage as networks are deployed out. But we would be looking at the time required. If we're looking at 3 years to have that as a requirement to be able to support all the multiple bands, those would be requirements going into our next generation RF chipsets, and then the time required for development, testing, and everything else, which is as I mentioned, is roughly a 3-year time frame to be able to do that.
I guess my question to follow up on that, though, would be when that current generation of chips was born, what was the thinking to make it non-interoperable? And we heard about the technical challenges in the first panel. Obviously, there are some legitimate technical reasons and difficulties to surmount, ones that can be surmounted, but the question remains, was that the right decision to make at the time? And that's something for the engineers to speak to, and they did very eloquently in the first panel, but it's a question that we have to look at as the Commission goes forward, not just simply cementing in the mistakes or the increased cost for competitors that were built into the current generation of chips, but looking at ways to improve that and to lower costs for consumers and for competitors going forward.
A question for Michael with regard to the sort of on a going forward basis. I mean, in the first panel, we heard about carrier aggregation and the beginning and the technical standards bodies of moving forward on that. The question of sort of what bands that one's going to think about aggregating to the extent that you're starting now with regard to the next generation of chipsets, and the question of sort of what you include and what you plan for. We've heard about the problems 2 and 3 years ago with regard to the interference issues. The question of now that we've come with band class 12, we have a sense of an approach to deal with those issues on sort of on a going forward basis where we start talking about carrier aggregation. How's that being taken into account as you folks and potentially others work on chipsets and other parts of devices?
Well, certainly, as we've worked closely with the carriers and specifically the Band 12 carriers, I mean, we've heard the requirements that they have. I can't speak here for our engineering and product management groups, but those are certainly considerations that we look at as we're doing planning. I think as was discussed earlier, I mean, in some of these cases, we're looking years out. So we make our best effort to plan and to try to understand the requirements that will be coming forth and to implement those into our chipsets. Now, I should also add that, as we look at the capability, the vast capabilities of multi-band, multi-mode, devices that come out and what we enable on the chipsets, it's really up to the OEMs to decide what it is that they will enable. And what drives the OEMs is demand coming from the carriers. As we've worked closely with the carriers here, a big part is getting the component vendors lined up. From the Qualcomm side, we've put mini specs in terms of defining the specifications that we see on the components. But the other critical part of that is to be able to have the demand coming from the carriers to drive that. So that's where we look, and that's what we have been messaging to the carriers is help us drive what you need, because our goal is to provide you with the solutions that you need in the marketplace. Help us do that by driving demand through the OEMs back into us, so all the rest of the ecosystem falls into place based on the demand that the carriers drive. Because we are absolutely in the business of providing the solutions that they need. So I think from our perspective, we look at the requirements going forward. We try to look into the crystal ball as much as we can and implement those requirements. But as folks know in the ecosystem, it takes time for testing, for implementation, for design. I mean, 3 years to do RF chips. There's a lot of investment and time required to make that happen.
Yeah, if I might briefly. Michael's exactly right. Qualcomm's a global business, and as Paul said on the first panel, this 700 megahertz issue with LTE and the band classes is a uniquely U.S. issue. I'd have to look to Michael for the answer here, but I would imagine that AT&T and Verizon are probably 8 or 9 on the size of your global customers. Where does that put band 12? And so if the band classes in 700 megahertz are allowed to remain non-interoperable, and there is no requirement that scale be aggregated, then you look at this on a global level, and it's easy to see why support is lacking for band 12. If the 2 largest carriers in the U.S. only rate 8th or 9th or 10th, whatever it is, to Qualcomm, we have to have a solution here, a required interoperability solution, in order to aggregate the scale and to drive this forward. Last week, RCA, the Competitive Carrier Association, had its convention and had a panel talking about 700 megahertz. And a question posed to the panel at the very end was, if the FCC does not require interoperability, how do we get it? And there was complete silence from the panel. There was no answer there. Nobody had the answer. So when you look at a scale-driven business and you realize where this problem rates globally, it makes more acute the need for an interoperability solution, an interoperability requirement from the Commission.
To follow on, we have another question from the audience. It's very relevant, Eric, to what you were saying. You mentioned economies of scale for handsets. In your discussions with manufacturers, have they provided an estimate as to the number of handsets required to achieve scale? And I think I would add to that also, how is scale actually defined? For example, if you have 2 handsets that are exactly the same with one difference between the 2 in terms of maybe a band that they support or whatnot, can we say that we can achieve scale with that one minor modification? Lastly, this question asks sort of the bottom line question, which is what is the increased cost to provide interoperability in the handsets? Which I think is the question we all need to get at.
So let me, I think hopefully it's evident by the fact that as we talk about our commercial samples coming out in September, we've heard loud and clear the requirements from the carriers that purchase band 12 spectrum. We are providing a commercial solution that is rolling out. So I hope that what we're hearing is Qualcomm has heard the requirement, heard the demand. We're in the business to provide those solutions, and we are absolutely doing so. In terms of the scale question, I mean, scale is always important in this business, but that's not the only criterion that we look at. I'll give some specific examples of small carriers having need for a low-tier phone that supports 1X advanced. This was we came out and designed another chip and came out with an additional SKU to provide that carrier specifically with support for 1X Advanced, and that was a small, a very small carrier. We've rolled out Rev B solutions in Europe in 450 megahertz. These are all very small numbers. So scale is certainly important, but we're trying to enable the entire, the entire ecosystem, all of the carriers. Where I think scale comes into play is when the carriers are working with their OEMs in terms of what they can drive. But certainly from Qualcomm's perspective, we're supporting and driving the commercial solutions as needed. See, I think you had another part to that question I'm missing. Or did I cover it?
I think, the bottom line costs. I mean,
costs. I mean, certainly that's a question that would need to go to the OEMs. We provide them with the chipset, so we're a part of the ecosystem. The OEMs working with the carriers would certainly be able to provide those costs. I can't. We're not in a position on our side to be able to provide that.
Question from the audience, although I'll retranslate a little bit, and that is, in the first panel we heard the question of Channel 51. We also heard about the issues raised by, the Qualcomm media flow uses of channels 55 and 56. If those issues were dealt with, how quickly could we actually come up with sort of interoperable chipsets, handsets, and achieve sort of the interoperability vision of 700 megahertz, if we were able to get there?
Well, certainly the deployment of supplemental downlink in channels 55 and 56 helped the situation in terms of what we had with interference before. So that's certainly a positive for the situation. As I mentioned today, we don't have the technical capability, so I can't give you timing on a solution that we don't have technical capability of today in terms of adding additional 700 megahertz bands to our RF chip. I mean, from the Qualcomm solution with an RTR 8600 on the RF side, we can only support a single 700 megahertz band in there.
And I guess there's an observation, and again from an audience, about the 3-year time period for developing chipsets and the like, and an observation, and you can correct this statement if you think it's wrong, and that is somebody's observed that it appeared that band 13 chipsets were available much sooner than 3 years after than the specifications and the technical standards were complete. And so comparing that versus statements in terms of how long it takes to develop chipsets.
Well, I can't give you the calendar specifically on band 13, other than the carrier that's deployed in band 13 was engaged with us quite some time ago in terms of driving the requirements. Certainly much sooner, because I think the auctions took place beforehand, so they were driving very quickly with creating demands and whatnot. Hopefully what we're seeing from the band 12 carriers is that we have been, very responsive. There were some very significant technical issues that had to be overcome specifically in band 12. We've been working with them for some time, and based on their requirements, going back months and months, and probably in most cases either weekly, if not daily conversations, we've been able to provide them with a solution to date. We don't develop band support serially. The requirements coming from different bands come at different times, and we also have, as we throw our resources at providing solutions, we're not able to get all of the bands all at the same time. There's an extensive amount of testing, the RF drivers and so forth, that have to be developed and tested. But the only reason that we would have a band 13 out prior to a band 12, one is just because of the timing when we started on that, and when the specific carriers were coming to us to work out and to drive solutions there.
Just to add on to that for a second, though, I mean, the implications of that are that scale isn't everything, but scale certainly helps to determine priorities, and so obviously there are technical reasons and other reasons for proceeding as Qualcomm did diligently to get all these answers out there into the marketplace, but that even if scale isn't everything, it does help to determine priority, and maybe it's no surprise to anyone, but the biggest carriers get to go first because they have more resources and also more of that demand aggregation ability within their own ecosystem within their own customer base than do other carriers who we hope at least can compete against them on a level playing field.
Did you have any other questions? Well, why don't we, since we have a few minutes left, why don't I give the panelists an opportunity for raise any sort of closing issues that hadn't been raised. I'm glad we took that opportunity in the first panel because Edgar might not have raised the band class 13-14 issues that the discussion hadn't covered. So I want to give the panelists an opportunity to raise any additional issues. So why don't we go in the order from the original presentation. So Stacy?
Thank you. Well, I guess the only question that I would pose, and it still kind of vexes me, is what's the problem we're trying to solve here? I mean, interoperability. Why is it just limited to the 700 band? People are doing deals with LightSquare. Should that be now something that is required to be put into devices as well? So, where do you stop? I mean, where does this discussion stop? Do we have to start making devices that are backwards compatible on both EVDO as well as WCDMA? So I'm perplexed as to the focus on 700.
Fortunately, I am here. The light squared issue is an easy one. Light squared operates at the L band, which has a single band class. AWS at LTE is a single band class. LTE at PCS is a single band class. And LTE at cellular is a single band class. CDMA at 850 at cellular is a single band class. It goes on and on. It was only when we got to 700 megahertz that the air interface technology took on multiple variations of band classes within a common spectrum block. And so the solution is, if you build a device to operate in a band of spectrum, you make it interoperable within that band of spectrum. If we choose to build a device at cellular, it will be interoperable across cellular. If we choose to build a device at 700, we should all make those devices interoperable across 700 megahertz. The lack of interoperability, it limits our deployment because we can't acquire devices in some instances, and certainly not at costs that would allow us to do a full-scale deployment as we have historically. And one of the fallacies is that you have to be one of the largest carriers in order to drive innovation, and it's simply not true. When we launch our LTE network, limited though it may be, we'll be launching a VoLTE network. We'll be delivering voice over LTE at launch. We're pretty certain we're going to be the first in the country to do that. We might be the first in the world to do it commercially, and we're a sub 900,000 customer carrier based in Ridgeland, Mississippi. That's our global headquarters. We also have 48% smartphone penetration in our customers. 48%. Almost every other one of our customers carries a smartphone, and this is a real smartphone. And we're talking about smartphones that do email, run apps, and have full web access. Not some other definition that allows us to count some feature phones and not others. I don't know everybody else's numbers, but I haven't heard of anybody close to 48%. In fact, I haven't heard of a number that's even half of 48%. So limiting innovation is a significant problem when we don't have interoperability and when we can't roll out next generation networks. And finally, I just want to touch on the Channel 51 issue. Never let it be said that there's something on which Verizon and Cellular South don't agree. We agree something needs to be done with Channel 51 and limiting, certainly restricting any new Channel 51 broadcasters and finding a solution for existing broadcasters. It's not a problem that causes irreparable damage to the A block everywhere, but it is one that would significantly increase the utilization of the A block if it were remedied.
Michael, before you begin, it seems that the audience is very interested in asking questions that are relevant to Qualcomm and your area of expertise. So before you start with your closing comments, maybe you can consider the following couple of questions that came in. Question about implementing multiple bands, for example, band 12 and band 13, using an RF switch in the device. And again, this is something that might add cost, or both monetary cost, but also cost and performance to the device. And just wanted to get your thoughts on how those cost and benefits weigh out. And another question is related to assuming AT&T's purchase of your D block spectrum and E block spectrum goes through. Wondering if it will take 3 years to develop a chipset solution for that particular implementation once the deal is closed.
So, talking specifically about the solutions that we're able to provide. Certainly you can start adding additional RF chips, duplexers, and so forth to devices. That adds cost. There's an impact to battery life, and that's when scale would come in for the OEMs. As the carriers know, they drive their OEMs very hard to drive the last dollar out of all of those devices. So I can't speak for the OEMs in terms of what they can provide from a technical solution. Certainly many more chips can be added, many more antennas can be added to devices, but those aren't devices that are commercially viable in the marketplace. With regard to the D block and supplemental downlink, I don't have a roadmap in terms of what our support is on that front. I think I don't know what the timing is for AT&T. That'd be a good question for AT&T in terms of when they roll that out. But our position on all of these technologies and all of these bands is to support as much as we can to the extent possible, to the extent that we're technically able. It's in our best interest to support that. It's in our best interest to drive chipsets into the marketplace and to support as many of these devices as possible, which I believe has been reflected on the roadmap that I showed with the multiple band. To Eric's point, we've got to tip our hat to Cellular South for a sub 900,000 subscriber carrier. They've certainly been able to do some excellent work in Mississippi and their other markets. They've been able to launch the HTC Desire, or they've announced plans to launch it anyway. The RIM Playbook using a Qualcomm Snapdragon chip. So they're getting some of the most cutting-edge devices that are going out into the marketplace for smart devices. So if you look at what they're able to do, certainly we're right behind them in being able to support that. In terms of interoperability, we're enabling that in multiple bands, multiple bandwidths. It's very challenging to be able to put 700 megahertz, AWS, PCS, 850, all in the same devices, being able to be backwards compatible with 4G, 3G, in some cases 2G. So we're supporting the ecosystem as much as possible, providing interoperability with multiple bands. Certainly here, the interest in being able to have multiple bands within 700 megahertz supported. That's a technical challenge that we have today, and certainly the demand and requirement will be considered going forward. But we are where we are today in terms of what our RF chips can do today from Qualcomm.
I guess I'll go back to the point too about where does it end, and the answer for today is that it does end with 700 megahertz interoperability. That's what we're discussing. We're not talking about some sort of Frankenstein's monster of interoperability that will be interoperable with everything forever and ever going forward and backwards, despite all the challenges that we've just heard about of making sure the devices work on multiple bands. But it really does end with 700 megahertz and the interoperability challenges we face there. We've heard today that the technical challenges are considerable but not insoluble. And we've heard that it's a matter of cost and allocating that cost fairly amongst carriers and really giving people a choice of devices is why our consumer groups are interested in these issues, because people benefit ultimately from having that flexibility to move from carrier to carrier to obtain cutting-edge devices on multiple carriers. So again, hat tip to the small carriers who are innovating in this space despite the challenges they face. That's the kind of thing we want to see more of, not less of, and that's what interoperability will provide us with, we feel, giving people a chance to compete on that level playing field within this band where so many broadband devices and services are springing forth.
Dennis?
As we said earlier, the challenge in public safety is going to be the fact that they operate today on regional carriers, on nationwide carriers, across 3G and now 4G technologies, and they're going to enter the mix with they'll be the third or fourth, I don't know how you count these things anymore, national operator of a network. So their problems are compounded in a significant way. So I believe that on the technical side, we're going to see a period where there will be a cost premium because of that complexity. Hopefully, as time goes on, that cost premium can go down. And the other thing is that the market being very non-monolithic means that there isn't a coherent governance structure. There's no single entity that can make business decisions for the community, and therefore the Commission plays a very important role, as do other organizations that represent public safety interests. So it is certainly a challenging endeavor, to say the least, that public safety is entering into. Thank you.
Well, again, thank the panelists all very much. If we could please give them a round of applause. So I wanted to thank them. I wanted to thank the panelists from the first session, and to all of you who participated here in the Commission meeting room and online. We appreciate your interest. This set of issues obviously is very important, policy set of issues to the Commission, to Commissioner Clyburn, I know to the Chairman and the other commissioners. So thank you for your interest in the matter. And again, thanks very much.